this was useful for understanding non-scalar complex manifolds. Anyway, the first person, the existence of Hermitian-Young mules relating to stability was well motivated already in the 1977, around the time when I proved the Calabi conjecture, because there was two proofs for the Calabi about the Motoko-Yau inequality, one using the K-line symmetric, one used the stability tool. So I already thought that these two concepts should be linked, namely stability and the existence of the equation. But the question is how to prove it. So Simon Donaldson proved that such a connection exists on complex surface if the bundle is stable. The first time when I learned about Simon Donaldson's work was through my good friend Hitchen when I visited London. So Simon proved this statement when the bundle, the first case in his master thesis, is when the bundle is deformed from tangent bundle of the K-free surface. He used the existence of Taylor-Ritchie flat metric, the one that I proved, to be stable, to deform it, and then he proved existence. So there was a first evidence of the conjecture of the existence of equation is equivalent to stability. So Simon, the first attempt was based on the Calabi conjecture. Then he found a brand new method based on the Chern-Bott form to create a new tool to prove the existence. That was a really outstanding work. I think that was his thesis, actually. And then when Ken Woudenberg and I have been actually working on it, but we are working in the general case. So a year after Simon Donaldson proved the case for complex surface, we proved it to be true in general. And this is, I consider to be one of my really best work. The difficulty I encountered, with Woudenberg was more than Calabi conjecture, actually, because this is a system of equation, not a single scalar equation. The scalar equation, we have many more methods to handle, but the Hermitian-Young mules equation is a system. As we know from minimal surface, system is far more complicated than a single equation. So this is actually the first incident, I think, that we can solve a nonlinear elliptic system with no singularity. And this is a Hermitian-Young mules equation. So there was a great effort they finally achieved. And I must say that I'm very proud of this achievement. And the equality and all those things for the Chern number turns out to be a very effective method in algebraic geometry. Also, so immediately, Carl Simpson, who was a student of Wilfred Smith in Harvard, adapted our method to bundles with Higgs field. Higgs field was introduced by Nacho Hitchen in the case of Riemann surface, and Simpson, under the guidance of Wilfred Smith, generalized it to more general cases. And this is a very fundamental contribution by Carl Simpson. And the statement, the way that he developed the whole theory is exactly the same as Woudenberg-Yau argument. And this argument by Woudenberg and myself so far is still the only method that can destabilize a manifold if a bundle if the equation does not hold. Anyway, this now has become a large industry under the suggestions or the program of Carl Simpson in deformation of Hodge structure and all that. And nowadays, sometimes it's called nonlinear Hodge theory. So this becomes a powerful tool, even in number theory, where Gorbachev used it for Langland's program. Well, at the same time, in the as I said, in 1984, string theory becomes a popular subject. And the famous work due to Candelas Horowitz, Witten, and Strominger has made Calabi-Yau manifold to be powerful and important. So a lot of people were excited by the subject, but by 1987, when I arrived in Harvard, people considered the subject is dead. The physicists are very fashionable. When they see nothing really come out from them, they declare the subject is dead. So many people look at me in a funny way, saying that your subject is dead. Why the hell you still talk about it? So, well, fortunately, in 1989, I have a postdoc called Brian Green. He started to work on this problem suggested by Kumran Wafa and several other people, that you could have two different topological different manifolds, Calabi-Yau manifold, both of them, and they exhibit the same quantum field theory that is called A model and a B model. And this was a phenomena that sounds impossible in the first sight. And because one manifold has different OI number from the others, when we do a search for those manifolds, most Calabi-Yau manifolds at the point before 1989, the examples that we create, most of them has OI number negative. And we thought it's asymmetric because M and M pi has opposite OI number, the way it comes out. And so I don't believe that is true. And so Brian Green did not care about what I said. He worked with one of our student Placer together. He came in my office suddenly one day and said, this has to be true. He only worked with the manifold, the quintic, and he did the quintic, and based on some failure due to Gabner, he said, look, this has to be true. And this then was carried out by Frederick Candelas and his whole group in Texas, Austin. And their calculation was amazing in 1989. And this was truly convincing job that changed the whole subject for me. And this was carried out in a very successful way because the mathematicians were very excited because they have been able to use that to calculate the number of rational curves over a quintic. And of course, this was generalized later to much more general cases. At least in the special cases, this was proved rigorously by Giventau and by Bonner and myself that what Candelas AL and also what Brian Green and Placer did was actually rigorous, can be rigorous proof, despite the argument was not their argument, which was based on quantum field theory. So this gives an indirect argument to say that the intuition that comes from string theory is actually good, that we can actually prove that is true. The intuitive consequence that comes from meter symmetry was hand-waving, to say the best. And we proved those hand-waving arguments actually can be proved rigorously. So I think this becomes a good place to do algebraic geometry with physicists. Well, this concept of meter symmetry has changed the view of many algebraic geometers. In 1990, we had a big conference in MSRI where all of my algebraic geometer friends, including David Morrison and all this, were very excited about pointing out how wrong the string theories were. And I was amazed to see how much they were pointing their fingers, how excited they were. Anyway, it was found that they were wrong instead. So in a matter of a few months, David Morrison becomes a true follower on meter symmetry, and ever since working on this subject for the last 40 years. And I think the development is great. Meter symmetry developed a method to calculate rational curves, but then we want to use this to look at higher genius curves too. There was a major development by 4 physicists. It's called BCOV. Jacobi is actually in Tsinghua. Anyway, these 4 great physicists, and largely all of them relate to Wi-Fi one way or the other. And so we were interested to calculate higher genius curves. This is called BCOV theory. Well, this leads to many, many intricate, delicate questions, including the definition of them. And this many people work on it. And Yamaguchi and I also work on this, my Japanese postdoc at the time. We found a way to understand these algebraic relations. And I think what we did is actually useful, and I believe they could be important for number theories in the long run. I mention it because I believe these partition functions who has integer source coefficients should play an important role in number theory in the future. But anyway, there are a lot of people working on how to make sure this definition is rigorous. And here I mentioned a few of them. Well, another major development was the understanding of meter symmetry. There was an understanding by conservatives called homological meter symmetry, which is a bit too abstract for me. I prefer the argument that Alex Saslow and I start with, and then Schlumberger come in. So this is the paper that we did in 1996. We observed that meter symmetry is basically some kind of Fourier-Mackay transform on several interesting bundles. So we think that the special Lagrangian cycle and could be used as a way to turn around one manifold to another manifold by flipping the toroid to the dual toroid. And this becomes the geometric interpretation of meter symmetry. This is 30 years ago, 1996. And I think this is a really important development because this put the abstract meter symmetry in a really geometric firm ground. The SYC program was not completely carried out, but many of the important steps has been verified, and most of them are important in the concept of geometry. So it could be looked at as so-called Fourier-Mackay transform, and let me not get into that. Well, many important equations and mathematical tools were created by looking at this SYC program. There are many of the important people has been making contributions to it, including Hitchen, Richard Thomas, who was my postdoc at the time, and Conan Leung, who was my student. They make important contribution to this SYC construction. And out of this SYC construction, Conan Leung, myself, and Sasso create a set of equations for bundles. And right now we are working on it. And for the past decade, many important Chinese and also students of Fong has been making important contribution to this equation. And this equation is more related to quantum physics. And I believe it would be important enough to replace Hermitian-Yang-Mills equation in the long run. Well, so let me remind you, in the 1920s, Elie Cartan created the concept of holonomic group using parallel transportation. And Ambrose Singer was able to understand the Lie algebra, the holonomic group construct in that way by using curvature tensor. And Marcel Berger then classified all the possible holonomic group. Then when the holonomic group is SUN, these are the Calabi-Yau manifolds, and there are holonomic groups like G2 and spin 7. So far, we have been talking about holonomic group equal to SUN, but equally important is the construction of G2 manifold. This is still a very mysterious manifold. The first non-trivial example was due to Joyce, using some singular perturbation argument. And this is unfortunately not well studied up to now. Well, another important landmark in the 1970s was the creation of Ritchie flow due to Hamilton. And here, one had to study the singularity created by Ritchie flow. Peter Lee and I have been contributing to it with Hamilton. Then using that to study many important phenomena that are created by Ritchie flow. And during 1980s, we have a group of students, my students, working on this subject immediately. And of course, as I said, in 2002, Perelman then improve some of this estimate and create something called entropy and reduce length and reduce volume to control the evolution of singularity. These are extremely intricate arguments, and is finally carry out the program that Hamilton wants to use. And this gives you the proof of the Poincare conjecture as we know it. And of course, in developing the Ritchie flow, Hamilton and Hodgkin already looked at the mean curvature flow to try to compare these two flows to understand the Ritchie flow. And I've been working with Hamilton for quite a long time on this. This is for parabolic equation and elliptic equation, but for hyperbolic equation, there was a great work due to Christodoulou and Kahneman, and they have been doing many important works in these directions. And I don't have much time to really put in that. But I would say that we are looking in the future. The future, as I said, would be several important questions in geometry. One very, very important question in geometry is the Hodge conjecture. And the Hodge conjecture, I believe, can only be solved by analytic methods, and namely through variational method. And manifold with high codimension will be key. And the high codimension singularity really was accomplished by Frederick Fleming and eventually by Fred Armgren in the fundamental landmark paper on the regularity of the minimals of varieties. And my friend Lian Sang has been giving a profound understand this singularity structure. The understanding of singularity structure would be important for the Hodge conjecture, I believe. Well, anyway, after 50 years, geometry and analysis and physics have been intimately linked, and geometric analysis, mathematical physics, algebraic geometry, and nonlinear partial differential equations are all nourishing one another. And after 50 years, Calabi-Yau manifolds are still the most natural high-dimensional generalization of elliptic curves, and many functions arise from string theory clearly relate to automorphisms. I hope that the 21st century, the relation between geometry and number theory will be discovered and developed. And there are many other interesting questions we can look into, but I would say that these are, we are following the great tradition by Riemann, and we hope that in the 21st century, we can see the development of geometric analysis towards physics, towards technology, towards understanding of quantum field theory, and all this will happen. Thank you.
Sorry. Are there any questions? you briefly flashed on a slide showing Frederick Albert. Could you go back to that?
Sure. Huh?
Frederick Albert, I think, was another example of someone who didn't get so much credit during his lifetime.
Oh, absolutely. Fred Armagon is a great geometer, a great analyst, one of the best in the 20th century. But he was so arrogant and mean to other people. she did not get the credit that he deserved. But nevertheless, I think Fred is one of the greatest geometers.
Any questions or comments?
Yeah. Here, Dan. What?
Do you think the Hodge conjecture is true?
No. Well, there are people who claim to be able to prove it for abelian varieties. Even for abelian variety, that would be great, but I don't believe it's done.
All right.
Professor Yao, a great honor to raise my question. If you were to point us students to one specific direction in geometric analysis, which is most likely to yield breakthroughs in the future, which problem or area would you like to recommend? Thank you very much.
Well, there are actually two problems I would be excited to solve. One is the Hodge conjecture, as you probably can tell. The other one is a conjecture that I make myself, that any almost complex manifold with complex dimension bigger than or equal to 3 emits an integrable complex structure. I'm not sure it's right, but I think it will be exciting if it can be done. If it's true, it would be more important than Hodge conjecture. That's my personal bias, but I think it's important.
Thank you very much.
At the end of your talk, you mentioned there could be some potential link between geometry and the number theory. Could you elaborate more on how to develop this direction? What was the intuition behind?
Well, dynamical system geometry has been developed all the way back to G.D. Birkhoff. Namely, his student Higland actually studied geodesic flows on manifold negative curvature. He proved it's ergodic and strongly mixing and all that. So it's not new that dynamical system enter in geometric analysis. The question is that how you develop it in the right way. Okay. It's not new, as I said. It's exciting that it's developing, but it's not new.
Thanks.
Say something about what's going to happen in the next 50 years rather than.
Well, as I said, I think understanding of the famous solutions in geometric analysis can be used to prove famous questions similar to geometric analysis. I hope you will develop geometric analysis.
You think that there will be a revolution in theoretical physics combined with mathematics?
Oh yeah, that's another thing I hope will happen. As I said, I hope number theory can look at all these very interesting consequences of beautiful generating function, as I said, that appears in string theory. I think they are very beautiful and should play a role in number theory. Okay.
All right. So let's thank our speaker again.
As I said, we can prove that this partition function can be built, as Yamaguchi and I saw, can be generated by only 5 generating functions, which I think is very important. Why that could happen, I think is an interesting, mysterious effort to understand.
Right.
So I think the number theory should look at it in more detail. Okay.
Thank you, Professor Liu Simon and Professor Yao. This will be the morning session, and that's all. Let's give him a round of applause. Yes.
Okay.
Let's go. Okay. It's okay. It's okay. I'm so sorry. I should get a chair or something.
Yeah.
Come on, please help.
Okay, it's okay.
It's my fault. I should give you a chair.
Well, this afternoon, we will start with Caucher Birkar, who has been with us for more than 4 years now, by now. 5. That's right. So he has been a great opponent for us. really changed our outlook to everybody. And also, she has taken care of our students in an amazing, important manner. And we are grateful that he is here. Well, she's an expert in algebraic geometry. Algebraic geometry is, of course, extremely important for geometric analysis. Most of my work are related to K geometry and in particular the algebraic geometry. So this is the most fundamental for the subject of geometric analysis. And I think everybody understands it. So the first talk, therefore, will be given by him, Altering Families of Algebraic Varieties and Applications. Thank you.
Good afternoon, everyone, and thank you, Professor Yao, for the kind introduction and for the invitation to give a talk at this really nice conference. So I'm going to talk about algebraic geometry. I will essentially talk about a theme in the field which has to do with families of algebraic varieties. So let me just first maybe fix some notation. A family will just mean basically like a fibration or a flat morphism, where we assume that the members of the fiber, they are all projectives. Basically, this is like a family of projective varieties, parameterized by some base Z, but mostly in this talk, I will look at the case when the base is a curve, because for many problems, even if the base is higher dimensional, you can reduce to statements about one-dimensional bases. So now the main question is, if you have a family like this, and assuming that you understand the general fibers well enough, so in many cases, they can be just smooth projective varieties. The general question is how the global geometry of the whole family relates to the fibers. In particular, how can we relate the geometry of the general members of the family to the special members of the family? Or in other words, one can also reformulate this by saying, if you have smooth projective varieties and you degenerate them, well, what kind of degenerations can you get? And maybe you put some extra assumptions and you want to control that degeneration. So this is a fundamental question in algebraic geometry, which also appears in many other areas, not only mathematics, even in physics. For example, degenerations of Calabi-Yaos are very important to understand mirror symmetry, for example. That's just one question which relates to physics. But from a purely geometric perspective, this is something that relates to many fundamental questions in algebraic geometry. So now, the theme of this talk is, if you are given a fibration, a family, or more precisely, I will actually talk about families of families, not just one given family. The question is, how can we make the family simpler, but keeping some data fixed or at least bounded? And this is related to making the family toroidal. So it's mostly related to singularities. We want to simplify the singularities on this family, but not in a kind of arbitrary way. We want to have some control of the family. And this is related to toroidal and toric geometry and log geometry and so on. But in particular, I also mention a few recent applications of these techniques to several problems in algebraic geometry. Now, I should also mention that making a family simpler is not a new thing. If you have just one family, for example, semi-stable reduction is a very a common technique in algebraic geometry, number theory, and so on. But what is new is that we are not working with one family. We have a whole family of families. So we want to simplify the families all at once in a uniform way. That is the key point. Okay, so let's just define more precisely what we are working with. So in many situations, when you have these families, the general fibers, you assume that you already understand them. For example, they will in some sense be controlled or bounded. For example, if you have smooth Fano varieties as general fibers, then you want to understand degenerations. And one of the places where this comes up is stability that was discussed in the morning, K-stability of Fano varieties. It's basically about understanding some, not all, but some degenerations of these Fano varieties. But this relates to many other problems. Okay, so let me tell you that we want to have control, and by control, I mean some kind of boundedness. We want to fix or bound some data, which I can formulate this in terms of degree or in terms of Hilbert schemes and so on. Maybe the degree is the easiest way. So on our family, we assume that we have some like a reference line bundle, something very positive, a very ample bundle, and we use that to measure how large the degrees of our varieties and cycles and so on are. So this is a pretty standard way. Just you can think of this line bundle to be like a hyperplane section. You use that intersected with all the subvarieties, then you can measure how large the degree is. As a very simple example, if you take like a hypersurface inside A1 cross P3, so this is defined by one equation. The equation itself has variables relating to P3. You can assume that this is homogeneous of a fixed degree, let's say degree 3. And then the coefficients will be polynomials in one variable. So if you fix the degree 3, then you basically have a family of cubic surfaces. If you have the degree 4, you have a family of K3 surfaces, quartics, and so on. So in general, it's essentially just like this, but you might have to take many equations, not just one equation. Okay, so we call this, when you fix the degrees or bound them, we call this phenomenon relative boundedness. It basically just means that the fibers are moving in some bounded family where the degrees are bounded. All the fibers, the general and also the special fibers. But the special fibers can be very ugly. They can be highly non-singular, highly singular. Okay, so now the task is how can we improve these families all at once? Okay, so you have essentially infinitely many families. One obvious way is to take any of these families and just do a resolution of singularities using Hironaka's work. But the problem is that although you can have control over the general fibers, but the special fibers, you basically have no control. Their degree will just usually go to infinity. They will be just too large. So this is not the way to go. And this is actually the first step of doing semi-stable reductions. In that case, you have just one single family. You do one resolution of singularities and you take some covers. That gives you a semi-stable reduction. But now, if you have infinitely families like this, then you lose control on the special fibers. The degrees will just increase and increase. You don't have any control. So that is not a good way to go. Instead, we have been using techniques coming from log geometry, or more specifically nodal curves and toroidal techniques and so on. So using these techniques, we can change the family into something simpler, simple enough, but we also control the degrees, we control the boundedness. So in this way, then we can translate many problems from a very complicated setting into a setting which is more manageable. Okay, so let's see what kind of singularities I'm talking about. These are called toroidal. A toroidal couple just means that you have a space, let's say X, together with a codimension 1 subspace, or a divisor more precisely. And if locally, formally, this is, let's say in analytic geometry, if this is just like a toric variety together with the invariant sub-variety, then we call such spaces toroidal. So it means locally, analytically, it is toric, but globally, it may be very far from being toric. So you only have a local kind of control of the singularities, but globally, this can be, for example, can be of general type. It may have nothing to do with toric geometry. Okay, so this kind of toroidal couples or pairs, they have very nice property. One is that the local, as I say, locally singularities are just like toric. So you can use toric geometry to understand them. And also the canonical bundle plus this boundary divisor is actually Cartier. It's locally given just by single equations. And this is something usually very difficult to achieve unless you work on smooth spaces. So now the idea is that if we start with a family, let's say X to Z, and even if we include some subspaces, some sub-varieties or divisors or a whole collection of them, we can change this family or alter it in a uniform way so that we get a new family where the new family is toroidal. And moreover, we can control all the degrees so that our fibers will still be moving in some, basically in some fixed projective space with the defining equations having bounded degrees. And moreover, this new family will be also toroidal. So that means that not only the total space is toroidal, but actually the morphism itself, locally, analytically, also will just look like a toric morphism. So we will take advantage of all this local simplification to translate many problems into toric geometry. Okay, so let me state this a little bit more precisely. Suppose that we are looking at families X to Z or XT to Z, and assume that this is relatively bounded. So this means that I'm looking at all possible families where the data is fixed. So this is not just one family. Then there exists an alteration. Alteration means that you have a diagram like in the picture where the morphisms mu and pi, they are generically finite. They are alterations. In algebraic geometry, these are called alterations. So they are similar to finite morphisms, but not exactly finite, a little bit more general, but these are called generically finite. Okay, such that the family on the left is going to be toroidal. As I said, that just means locally, analytically, this is just toric. Moreover, the family on the left also will be relatively bounded. And moreover, these alterations that we take pi and mu, we can also control their degrees. This is also not arbitrary. So they are just like finite morphisms. Their degree is also universally bounded. And moreover, if anything goes wrong in this family, they will all be inside the boundary divisor. So this is also quite important for applications. More precisely, if we remove the boundary from X prime, so this naturally will map to X minus D, and this will be quasi-finite. So this means it really look like a finite morphism where you don't allow any curve or surfaces or whatever to be contracted. So this is important. So it essentially means that anything that is kind of interesting in this diagram will be part of this boundary divisor. For example, if you look at the special fiber of X prime to Z prime, or even X prime to Z, that will be also inside this boundary divisor D prime. So we can then control basically everything that we want using this new family. Okay, so maybe I just try to give you a very rough idea how you construct this kind of families, these alterations. The basic idea is that because we are working with a relatively bounded family, then we can find a universal family. Let's call that curly X to curly B, or I could say curly Z, where all our families are pullback of this universal family. So this is just a simple application of Hilbert schemes and so on. Okay, now the idea is to go and do something with the universal family first. So we change the universal family itself into a tower of morphisms, or a tower of vibrations, where in every step, the morphism, let's say from Vi to Vi minus 1, is a family of nodal curves. So this is something very familiar to people who work on surfaces, for example. If you do semi-stable reduction and so on, this is exactly what kind of thing you get. You get a family where the fibers are semi-stable, they are nodal curves. But this is higher dimensional. And we have a whole tower of this kind of families or vibrations of nodal curves. And the idea is that inductively, so assuming that on the very base, V1, C1 is something that you already understand, it is toroidal. In fact, usually you can take this just to be smooth. And then inductively, V2 to V1, you show that this also has a toroidal structure. And then you go to V3 to V2 and so on. Just inductively, you need to make sure that locally, analytically, everything looks like toric. So once you do that, then what you can do is for your original family X to Z, which is a pullback of the universal family, then you kind of just take like a product. Then it will naturally transform the X to Z, the original family, into another family, which is also a vibration or a tower by nodal curves. Then it will automatically say that your new family is actually toroidal. It's simply because you have decomposed it into a family of a vibration or a tower of nodal curves. So that is the basic idea. And here, what I use is the de Jong theory of nodal curves, which he applied to get a new proof of the resolution of singularities, which is very different from Hironaka's original resolution. But the key new ingredient is this boundedness. We are doing this in a uniform way, not working just with one family, but with families of families. Okay, so now for some applications, this is already enough. If you get a new family where you have toroidal structures, that will be enough to actually prove some really nice results. But sometimes this is not enough, because these toroidal structures, they are just locally nice, but globally, their geometry is very complicated. So the idea instead is to pass to a genuine toric model. So that means, let's say I have originally X to Z. Okay, we cannot see the X to Z, but we have changed the X to Z to X prime to Z prime. Here we have this toroidal structure. Okay, so locally, we know everything is nice, but that is not enough. So we want something that also globally look like toric. And then what we can do is, using some et al. Kind of covers, at least locally, we can find a new vibration or a new family where this new family is actually genuinely toric. And then we can try to translate problems from the toroidal setting into this toric setting. And there we can use not only local toric geometry, but we can also use global toric geometry. And this is fundamental for some problems. As I say, sometimes you don't need to go this far, but some problems just force you to go onto the toric model rather than just the toroidal. Okay, so a bit more precisely, there will be like a common étale cover locally between the X prime, the toroidal structure, and the toric structure. And the fact that this is étale at some point means that immediately tells you locally, analytically, they must be the same. And so you have the toric global structure, and moreover, here also you have relative boundedness. Again, you control all the degrees, even in the toric situation. And for a diagram like this, we just say that this Y prime is a toric model of our toroidal structure. Okay, so what you get in the end is you can translate many problems which are of a local and even sometimes global nature from the very original fibration family, which might be pretty complicated, into toroidal and then also toric. So that allows you to use toric geometry to solve problems that they don't seem to have anything to do with toric geometry. That is the whole point. Okay, so I will then try to show you 3 examples of applications of this technique. So this is just a sample. I'm sure that this applies to many other problems. One of those problems is related to Fano fibrations. So that means that we look at families X to Z, which are Fano. Fano means that minus the canonical bundle is positive or ample over the base. And a fundamental conjecture in this direction, this has a longer history, but the most general form is a conjecture due to Shakurov and some form of it due to McKernan. It basically says the statement, you can make it simple, although the full statement is more complicated. It essentially says that, well, let's look at the Fano fibration. Okay, so this could be, for example, a family of Del Pezzo surfaces where the general fibers are Del Pezzo, but the special fiber, it may not be even irreducible, or it may not be reduced. So it's usually more complicated. Okay, but plus one global assumption. We assume that the X itself, it has nice enough singularities, which I'm not going to even define it, but just think of it as some kind of measure of singularity. We call this epsilon low-canonical or epsilon LC. So the conjecture says, if you have such a fibration, if the total space has nice enough singularities, then this forces the base also to have nice singularities. You cannot have like arbitrary or even ugly singularities. It forces the base to be really nice. And moreover, for a moment, let's assume that the base is a curve. The conjecture also say that all the fibers must have universally bounded multiplicities. So one is about singularities of the base, another claim is about the singularities of the fibers. And this Fano condition here is quite important, because if you pass from Fano to Calabi-Yau, then this immediately fails. And an example is elliptic surfaces. If you look at elliptic fibrations from surfaces over curves, if you don't put any extra assumption, even if you assume this is a minimal elliptic surface, then the multiplicity of special fibers are not bounded. They can be arbitrarily large. But actually, that's not the end of the story. So we realize that even in that case, you can prove something similar. What you need to do is to assume that you have a multi-section which also has bounded degree. Then that also forces all the special fibers to be, in some sense, bounded. So this obviously relates also to number theory and so on. Okay, so the statement, as I said, I have simplified as much as I could, but the proof is actually much more complicated than what the statement looks like. So I'm going to kind of condense everything just into some really simple kind of remarks. Okay, so how do you approach a problem like this? Well, one technique allows you to reduce the whole thing to the case when the base is one-dimensional. So this is more or less standard. We already knew that from many years ago. So the problem is really about families over curves. All the difficulties are already in that case. Okay, so now such a family is not relatively bounded. In general, there is no such thing. But however, if we apply the so-called BAB conjecture or boundedness of final varieties, we have a generic boundedness. So let's say if the general fibers are smooth del Pezzos, then we know that they are bounded. But the special fibers, we have no idea. Okay, so the idea is to use this generic boundedness plus another tool, which is called complement or complement theory. This is basically about, if you are on a final variety, it's about looking at the linear systems minus nk and show that for some universal n, minus nk always is non-empty, and even it has a really nice element. This itself is a whole theory, so I'm not going into the details. But anyway, what you get will be a structure like this. You have your x, it gives you a boundary divisor so that x and the boundary together, they have nice singularities, plus this extremely important condition that for some universal n times k plus lambda is a pullback of some Cartier divisor. So that means that it's locally defined by some equation, but locally over z, not locally on x. And this is what really all that makes all the difference. It essentially tells you you are going from a situation which is completely wild to a situation where in some sense it looks like discrete. And these kind of structures are really difficult to come by. But fortunately, we already had this theory. So we impose this structure on our vibration, but still this is not relatively bounded. However, generically it is, so we can pass to a birational model where we have this relative boundedness. And the idea is to work with that other family. Okay, so now because we have this model which is relatively bounded, then we can apply our toroidal techniques and alter it to a new, still relatively bounded family, let's say x prime to z prime, where the singularities are much better than the original setting. Okay, but for the problem that I mentioned, these singularities of final vibrations, this is actually not enough. Just to get to the toroidal model actually gives you very little. It's locally nice, but you really need some nice global geometry in order to solve the problem. And that kind of goes through defining some structure over the toroidal model, some birational structure, and then you have to pass to the toric model, which I mentioned before. And in the end, it allows you to pass to the projective space, but the projective space will be just like a base. You have essentially some model on top of the projective space, and you have to work with this model. But the advantage is that the original problem can be translated into a purely toric problem. So that is the whole process. You go from something which doesn't look like have anything to do with toric geometry to a problem which is purely toric. Okay, so usually in algebraic geometry, once you arrive at this step, then everything is nice and combinatorial and so on. But actually, in this case, it was not the case. This actually, it took me more time to figure this out than the rest. So even it's toric, but because it didn't look like any other problem in the literature, so it was really not very easy to figure it out. But anyway, so this was solved, and then that solves the conjecture that I was talking about. So it just illustrates how you use these simplifications, the toroidal and toric and so on, to translate a really difficult problem into something which is at least theoretically, is more manageable. Okay, so that was the first application of these alterations. So I don't think I will have enough time to explain everything, but I will go as far as I can. So now this conjecture itself, once it is proved, it also implies many other things. And that's the nice thing about this problem. In particular, it gives you another conjecture, which I'm not going to even state. When the base is a curve, it is also about Fano vibrations, but it's not so much about singularity. It is more about linear systems and so on. But it's even actually nicer. It allows you to completely reduce this new complement conjecture into the situation where you are in the local case. You are just essentially need to understand the singularities. So it translates a problem about vibrations into a problem about just singularities, and also it reduces the dimension to the dimension of the base. So that means, for example, if you have families over surfaces, that's one thing that my postdoc looked at, then even if the fibers have really high dimension, you are still reduced to the case of surfaces. So that really simplifies the original so-called KLT complement conjecture. Okay, another thing it implies is related to rationally connected varieties, where minus the canonical bundle is like semi-positive. It implies a kind of boundedness on such vibrations, on such varieties. So for example, this kind of rationally connected, for example, you can take rationally connected Calabi-Yau varieties. And these kind of varieties appear as degeneration as usual Calabi-Yau varieties. So in some sense, they say that all such degeneration should be, in some way, should be bounded. Okay, there are more applications to families of Calabi-Yaus, to the so-called Sarkiso program, and so on. And I'm sure there will be many more applications in the future. So let's try to get into the second application of this technique of making things toroidal. This one is about degenerations, which I mentioned at the very beginning of the talk. If you have a certain kind of varieties, well, what kind of degenerations you get? A very simple example is if you look at cubic surfaces, these are degree 3 surfaces defined in P3. Okay, so you can degenerate. The generation can be smooth, but it can be also singular. For example, they can degenerate into a cone over an elliptic curve. And what is interesting in this transition is that you go from a del Peso surface, which is actually a rational surface. The degeneration is not. So somehow you lose the rationality in the process. It's not even so-called rationally connected. So then a question in this direction is, a specific question is, if you have fibers which are rational, well, what kind of degeneration you get? Or if you have fibers which are rationally connected, what kind of degenerations are possible to get? But in general, if you allow arbitrary degenerations, there is almost no control. But you need to assume some, you need to impose some conditions. So let me make things, try to make things very simple as possible. If you look at, let's say, a Fano vibration, but actually this kind of thing apply even to Calabi-Yaus or general type and so on. As long as you have some control over the degrees, that the same thing will apply. But anyway, let's say we have a family of Fano varieties. Okay, globally, we need to assume the singularity are nice enough, actually, or just over the generic points of the base. And we take one of these special fibers. For simplicity, let's say this is irreducible, although this is not really necessary. Moreover, suppose that if we take the reduction of this fiber, then some multiple of this fiber together with the total space gives you some reasonably good singularities. Then one shows that then there must exist a dominant map from our fiber to some for example, smooth projective variety, where the fibers are all, the general fibers are rational, and moreover, the base will be in some uniform way bounded. So a special case of this, maybe easier to digest, is the case when our X has dimension 3. Then this is really just about families of Delpesos, possibly singular. He says that, well, if you look at this special fiber, which may not be reduced, but you just take the reduction of it, then it is birational to P1 cross some smooth projective curve. And the statement tells you that this smooth projective curve must have bounded genus. And that's the striking thing about it. If you don't impose these kind of conditions, then the genus of C can be anything. You can easily produce examples where the curve C has no bound at all. But with these natural assumptions, then you actually essentially say that, well, you have all these fibers which are already rational, so they are as simple as possible, and anything which is not rational is hiding inside this base. But the base itself is uniformly controlled. For example, the genus is bounded. So this tells you that although the fibers may not be rational, but how far they are from being rational is universally must be bounded. Okay, so let me try also in a few minutes to try to explain how we use these toroidal geometries to tackle a problem like that. So again, we have to go back to the theory of complements together with bounded and Zafano varieties. This gives us some kind of discrete structure relatively over the base. And moreover, we can assume that our fiber, our special fiber, or T times this fiber, is inside this structure. It's dominated by our given complement. And moreover, birationally, we get a relatively bounded model of our vibration. Then we apply these toroidal techniques. However, here we need something a little stronger in some sense, but weaker in some other sense. We want the new model to be birational to the original one. In the first application, this did not matter at all. You only need bounded on the degrees. If it is finite or generically finite, you don't care. But here it is essential to have something birational. And in order to obtain such a toroidal model, this technique of de Jong, then it doesn't work very well. Instead, we use log geometry, more kind of recent techniques to obtain this toroidal model. But on the other hand, is not as strong as de Jong's technique because keeping the data bounded is a little bit more tricky. But still, it's good enough. Is almost like relatively bounded. And then what we can do is we can go over this toroidal model. Because it is birational to the original one, our divisor, our special fiber F, now it maps in a natural way to some subvariety of the toroidal model. And also because you are working on a toroidal model, the fibers will automatically be toric. So they are automatically rational. But moreover, the base or the center of this divisor inside the toroidal model, you can also control that at least birationally, and you can assume that, you can prove that that is actually universally bounded. So for example, if it is one-dimensional, that means that the genus must be universally bounded. Okay, so that gives us the vibration. So in this application, as you see, just to have the toroidal model is enough. You don't have to pass to the toric model, which is much more complicated. Okay, and yet there is another quite different kind of application of the same type of techniques, and this relates to the so-called Stein degree. The Stein degree is something very, very basic, but it has only been kind of formally defined just recently. It first appears in one of my work on moduli spaces. So I needed this kind of notion in order to construct moduli spaces of minimal varieties, but the definition is quite simple. So it basically, if you have a proper morphism from, let's say, some variety S to another, or even you can take schemes, then the Stein degree just looks at the general fibers and count how many connected components it has. There is another stronger version where you can count the number of irreducible components. So in the language of algebraic geometry, for such a morphism, there is a so-called Stein factorization. That's where the name comes from. And the degree of the finite part is exactly this Stein degree. Okay, so what we proved with Santai Chu was that if you work on a Calabi-Yau vibration, but a more general, so-called low Calabi-Yau. So low Calabi-Yau means that canonical bundle plus a boundary divisor is trivial, not the canonical divisor. So in particular, this applies to all Fano vibrations. Okay, it says that if you have such a low Calabi-Yau vibration, let's say you pick some component of the boundary divisor, but assuming that this coefficient is not too small, then the Stein degree of this divisor or onto its image, so in the horizontal case, that will always be universally bounded. The only thing that it depends on is the dimension and this coefficient here. And kind of fixing this coefficient is necessary. Otherwise, you can just give trivial examples where you do not have any control over these degrees. But in the vertical case, it's a bit more tricky. It actually does not even hold. We have counterexamples, but at least if you assume your vibration is coming from Fanos in some sense, then it is also holding, at least when the image is of codimension 1 inside Z. Okay, so this is quite interesting that you get this universal bound on the number of connected components of the fiber. We actually prove something even more strong. We prove that the number of irreducible components is bounded. Okay, so from algebraic geometry and birational geometry perspective, this is something that really we want because it applies to other situations that are interesting. But what is interesting about this problem is that it also connects directly to arithmetic geometry. Now, if you work over not complex numbers or algebraically closed fields, if you work over number field, then the same kind of thing can be defined. The Stein degree has the same definition. But in that case, for example, if you work instead of divisors, if you work with points, then the Stein degree is precisely the arithmetic degree of your point over the ground field. And in fact, I have a version, a conjecture, essentially the same, more or less the same in the arithmetic situation. So if you work over any field of characteristic 0, then I conjecture that you have some universal bound on the Stein degree. And in particular, if you work not with divisor, but more generally with points, of course, you cannot take arbitrary points. Those points should be kind of special with respect to this structure, which is related to the singularities of this structure. It just says that where you have this type of singularities, like difficult enough, then the arithmetic degree of that point must be universally bounded. And I think that is really very interesting for especially studying rational points on algebraic varieties. And I'm actually working on this with some people, so I'm sure that this will have some sort of application to arithmetic geometry. Okay, so I think maybe not too much point to try to go through the proof of this because it's kind of, it uses similar techniques. So I'm just going to skip it. Okay, maybe I'll just mention in a few words that this technique definitely will have more problems. So let me problem control of data in many problems in algebraic geometry, but making this data explicit is usually extremely difficult. And this is a really important problem from the point of view of mathematics, even from the point of view of philosophy of mathematics. Just to prove that something exists is not always satisfactory. You want really to construct them. So this relates to constructive mathematics or computational as well. It's related to computers and computational mathematics and so on. So there are many, many problems that we don't have the answer. We don't have any effective techniques or bounds, although we have abstract ones. Okay, Stein theory over non-closed fields, I already mentioned. One really very hard problem here is to work out or to look at toroidal models in the local situation. So suppose you have just a singularity, a germ of a singularity. You can talk about toroidal model of such a singularity, but can you do it in a bounded way? For surfaces, actually, you can do. But from threefolds, we kind of have expectation that this kind of model should exist, but it would actually be very, very hard to construct. But if you can construct them, then it can solve many difficult problems. Okay, and then there are many other problems about degenerations, and this kind of technique should apply, not just to rationality, but to other kind of properties of global properties of varieties, and you want to see what kind of degenerations you get. Okay, so I will stop here. Thank you.
Well, great. It's a really beautiful lecture, and also shows important contribution of Professor Birkar since he come here. I think now he understands Fano manifold better than any other people. Probably the best contribution since Fano. And any questions for Professor Birkar? Well, if not, we are very grateful for the
question at the end.
Oh, okay.
Thanks. Do you see a story of tropicalization for bounded toroidalization?
Can you repeat again? I didn't get.
Is there possibly maybe some story of tropicalization of the story?
Properization.
Tropicalization.
Tropicalization. It's possible. Maybe if you take, usually in algebraic geometry, you have to like apply some kind of log to pass through the tropical situation. So maybe one can try. Well, if you pass to the toric, then from toric to tropical, I think that's more natural. So maybe, but of course the question is what you want to control.
Other questions? Okay, if not, first of all, I encourage our students to study with Professor Birkar. He has taken several students who has accomplished these all major important works. And I hope this continues the last 5 years. Thank you.
Thank you.
Okay. Let's continue with Shou-Wu Zhang, who I knew for more than 25 years, actually more than that, 30 years by now. So he wrote to me when he was writing his thesis, and what he wants turns out to be exactly the thesis I direct Gang 10 about the way to approximate K-line symmetric with polynomial with embeddings into projective space. And he developed into a great subject by himself. And I'm very proud of his accomplishment, especially he spent long time in Morningside Institute to develop modern number theory for the whole generation, more than one generation, 2 or 3 generations, produce the best number theoretical scholars in China, including Ye Tian, including Yuan Shengyi, and many others, and Wei Chen. And this is revolution for Chinese number theory, and I'm very grateful he has done that. And I'm expecting he's coming back to help. So, his title would be Geometric Analysis with Direct Metrics. Okay.
Thank you, Professor Yau, for introducing me. And I found I'm the only person to use geometry analysis as a title. And actually, I don't know anything about geometry analysis. I don't really know the theory, but I heard the name. It's a long time ago when I was an undergraduate student at the Zhongshan University in 1982. When Professor Zheng Shaoyuan visited me, he told me he had a great friend, Shing-Tung Yau. He proved a great theorem. Around that time, I studied number theory. So, in my generation, the hero is Zheng Chen. After, I think, when Yao came out, then everybody changed the hero to Shing-Tung Yau. Then suddenly he becomes superstar, and his gravity is very big, like a black hole, and get everybody jump to there. So I trying to be more independent and doing something by myself. Anyway, I come to Columbia to study number theory. Then somehow the Yao theorem is mentioned in the morning, called there's a C1 square less equal than 3C2, have a great impact in number theory. So somehow in number theory, there's the most important unsolved problem is effective model conjecture. These days it's called ABC conjecture. That should be the easy consequence of the Bogomolov-Yau inequality. So I started to look and trying to study Yau's work. Then my friend Huaidong Cao was there, and he gave a course. I guess I pushed him really hard. Tell me what exactly you're doing. Then he gave a course and talk about the proof of the Calabi conjecture. And of course, he used PDE. A few years later, I always trying to see if there's any way I can do it in number theory. So my lecture today is that you can work on the Calabi of this Calabi matrix without a PDE, but you need to use something else in number theory. So I wrote a paper on a complex place and a periodic place can be put together, become a family. This is a family called eidetic family. Inside the eidetic family, you don't need a PDE, but you need to control some numbers. Once this height is controlled, then you get both periodic Kallenstein and the complex Kallenstein simultaneously. Unfortunately, my paper not so successful. So one funny thing that if the setting from number field to function field, in fact, I get a positive number. Unfortunately, my paper is written just for number theorists. So many of my work was rediscovered by many other people. And so today I will explain. In fact, some of them can be used. Okay, let's try to, in my abstract, I try to talk a lot. Today I only want to study one problem. So I study family degeneration of the polarized varieties. That's a central problem in the algebraic geometry. So that's the family admit a canonical degeneration at t equals 0. That's the problem. The guiding philosophy is that degeneration problems should be related to non-accumulated metrics. So in this way, the idea of differential geometry can be used. So, okay, that's a problem. You have a smooth family of varieties, the previous talk. When you get a family, you get some singular varieties. You get a singular variety. You want a singularity as contains the hidden metric information. The central fiber records the symptotic equals 0. So I will explain why. What do I mean the geometry situation? So I will start non-Euclidean geometry. So a norm in the field is the usual norm. Satisfies a product property and the triangular property. The three norm, that's the concept use exponential order explain the Russian numbers. The third one actually is different. So this relates to three geometry together, or differential geometry, arithmetic geometry, and algebra geometry. So I will explain how the three geometry interact together. So, okay, let me do in a more algebra geometry setting. So it starts a field K, that is a Lorentz series. So it has a valuation I just defined. It just gives you a Lorentz series, just counting the first term. Then if I have a variety of K, is a scheme, right? It's just a family like that. Then, and the general fiber is X, the special fiber X0. This X0 is something we want to understand. So what I'm going to do is that I make this problem to be a metric problem, because I don't want to look for algebra geometry. I want use the differential geometry idea to study algebra geometry problems. So I translate the problem to differential geometry. What I'm going to change is that, okay, so for example, if E is a vector space of K, right? So then in algebra geometry, of course, you're looking for the integral models. So you want the E to be our lattice defined over a power series, not the Lorentz series. In this way, then you can define a norm on this E. Is the minimal A such that X is that AE. So this curved A should be unitable in the E. That's interesting thing in non-Euclidean geometry. In the complex geometry, of course, unitable doesn't have a ring structure. But in the non-Euclidean geometry, the unitable has a ring structure. So this is something to do with the different algebra geometry. So in this example, show you that the models which algebra geometry looking is nothing else than the metric structure. So I changed the language from the integral structure, which is used every day in algebra geometry, by looking for a metric in the complex geometry. So the principle extends to line bundles of varieties. If I have a variety defined of a Lorentz series, I put a metric structure there, which will more or less look like something at the integral structure. But once you be very careful, you have much more metrics than models. So this way give you a lot, much with a big flexibility than algebra geometry. Algebra geometry, you can only looking for certain closure, but the different geometry are looking for something much more than that. This is very similar to say, okay, I give you a bundle like a PN. You algebra geometry probably looking for forbidden study matrix, but different geometry can look for any matrix. There's something like that. You get much more metrics you can do. So, okay, so like I will talk a semi-simple reduction theorem, but this is important because I need to write down. So if you, for any variety of a complex number, you, by Hironaka theorem, if you allow the t to the 1 over t, then your variety could give semi-stable reduction theorem. The semi-stable reduction theorem means that locally it's given by a very simple equation. Then the logarithm cotangent bundle will be defined by dx1 of x1, dxr of r. So this way you get a metric. So this gives you one example. How do I get a metric? So this only happen if you have semi-stable reduction. This is why semi-stable reduction is used every day. Everybody talk about that. Otherwise, we're not going to get the good structure, integral structure, and the tangent bundle, cotangent bundle. Then I will take limits of metrics for models. This will be very technical. I will not explain. If you really look at it, there's the new book, I just published in a Princeton annual study, Shing-Tung Yau, I wrote it, called Identical Line Bundles of Quasi-Projective Variety. This explains how do I define a continuous matrix, how do I define the pluri-subharmonic matrix, and how to define the integral matrix. I will not going to explain that. The whole point is that with this kind of metric, if you have a line bundle with non-commutative norm, we can define something called a Shambhala measure. Once a Shambhala measure, we can talk about a mountain pair theory. So there's a non-commutative analog of mountain pair theory. So finally we put the algebra geometry in something the core theories in the mountain paper. That's not the PDE involved. So let L be an ample line bundle with a pluri-subharmonic metric. I mean, this means C1 is non-negative, basically means this way. Then we seek the analog of the scalar curvature, omega. This omega should be C1. C1 of this L bar will be a metric. The funny thing in non-commutative geometry, nobody knows how to define C1 of a line bundle. It doesn't make sense. We can only say that makes sense, the measure makes sense. But the individual metric itself doesn't make much sense. The one-one form does not exist. So anyway, so that's the definition of the scalar curvature, right? You have a omega supposed to be a metric of the tangent bundle or canonical bundle. Then you put this together. That's the definition of the standard definition of the metric with the scalar constant scale curvature. So this applies to special case. So L is omega x or omega x minus 1. Then this gives you a non-commutative Karl-Einstein metric. I mean, for Calabi-Yau manifold, this is not, you have to extra, you have to fix a measure and a variety, right? And for other two, you don't really need. Well, that's what I learned from Huaidong. So Yau's philosophy, at least in that time, is canonical matrix should be related to stability. That's something he explained there. And in my paper, I mean, I introduced the 3 ingredients which can be handled this kind of problem. I call it Chow line, Mapuche line, and height functions. Chow line is the following. If you have a lot of subvariety in the project space, then all the subvariety together with fixed degree form a variety called a Chow variety. This Chow variety, if we quoted by use GIT theory, quoted by general linear group, you get a variety, projective variety. There's a variety has a canonical line bundle. So each point there, we have a line. So there's a line I call a Chow line. So Chow line means the ample line bundle and the Chow variety. And the Mapuche line is another line. So if it's for polarized variety, if you consider all the powers, depending, you're supposed to get a variety. The Mapuche line is supposed to be also ample line bundle over modular space. And the Mapuche line is supposed to be the limits of a Chow line. That's how I can explain next slides. The most important thing, I will define height functions. This is quite important. In differential geometry, the functional usually is a relative notion, right? You need to fix a reference metric, then talk about the difference of them, you get a functional. But in identical geometry, you don't need reference metric. This is the points I can explain today. So algebra geometry mirrors the complex variation theory. So that's basically. So for example, I define a Chow line. You take X in the project space. Then use the Deligne pairing. The gamma XLN of the vector space, right? You can determine the line. Or I divide it by some positive number. So this is not a line, it's a Q line. Q line means that you multiply it by some integer, you get a line. Okay, so does it make sense? So in other words, a Chow line, if I multiply by denominator, I get a line. Or I use addition and subtraction denote tensor products. So I make the line, the vector space with the tensor products, I use addition because I only have one-dimensional vector space. So that's so a metric and L induce a norms of space of sections. So then, okay, if you have a metric, then there's a metric will define, and each term is same. It determines the gamma XLN, also make a metric and there's a Deline's pairing. So once you have a metric, I have a metric on this one-dimensional line. One-dimensional line is very nice. So just some line is what? It's a line with reference points. If you give me two metric, then I can talk about difference of them, right? So that's the point. So now I take the limits of a chart line, I get a Mapuche line. Mapuche line is defined by this way. This maybe when you do differential geometry, probably look similar, you know. It's also written in the Deline's pairing. It's one Deline's pairing minus another Deline's pairing. The metric L defined Mapuche functional. That's exactly found Mapuche function used in the differential geometry. But for me, is that I use a line. I don't never use a reference metric. So in other words, if I have a reference metric, then I can talk about Mapuche functional. The critical points here correspond to constant scalar curvature metrics. So I put this in non-accumulative word and accumulative word in same footnote. So finally, now is the key points. So before I'm doing that, there's almost no difference between differential geometry and algebra geometry. Here is the difference. Here, suddenly I'm changing my way to do that. I will not looking for one metric. And one metric, I cannot do anything. So if I do it, I have to jump to the PDE. What I'm going to do is I start with the compact Riemann surface. I let a K be the field of meromorphic function of this Riemann surface. So my K is not a valuation field anymore, right? My K is just the function field of algebraic curve. But this field has many metrics. For each point of the Riemann surface, you can talk about metric. So this collection is called adelic metric. Because each point is a p-adic, right? They put all things together, I call it adelic metric. Adelic metric means that it's a collection of metrics parameterized by whole Riemann surface. So, yeah, so that's all the metric you can have. So this is globalized non-Archimedean geometry. So original Archimedean geometry is one place, now it globalized. This idea is very common in number theory. For example, if you want to prove local classical theory, you have to prove global first. This is a very common sense. Even in a modern work, for example, the Harris-Taylor work is their proof of the Lagrange, the local Lagrange for GRN, they prove global. From global induce the local. I use a similar idea. I want to find a Klein metric. I have to use a global method, not local method. Because local method, your function has no reference points. I don't know how to do it. Global, I don't need the reference points. So once of global, I can define called heights. There are two heights I've involved. One the Chou heights, one the Mapuche heights. Anyway, suddenly become a real number. That's really amazing because originally I get a lot of lines. Suddenly all the lines together, I get a number because this is the degree of a line bound on a Riemann surface. Right? The degree of a line bound with a adelic metric, just a usual line bound on a Riemann surface, you can talk about degree. This is basically the degree I get. Not only that, my Mapuche heights is the limits of the Chou heights, right? So I get a dictionary. This is complex geometry. This is arithmetic geometry. I put a quotation there. This is really algebra geometry. I really didn't do PID number. There's a Mapuche functional, the Mapuche heights. Then constant scalar curvature metric, then become adelic constant scalar metric. Then the K stability become positivity of the heights. So I just one number, I need to prove the positive, that's it. Okay, now I really tell you what the theorem I proved in my composition paper 1996 is that I show that for n sufficiently large, I'm sorry, that I forget one condition. Oh yeah, I didn't find a condition. This number, the child height, is bounded from below if and only if this embedding is a child stable under this action. Moreover, in this situation, my number is non-negative. This last equation is very important, non-negative. If only bounded from below, say below bigger than negative 100, I'm not going to work anymore. Non-negative is cool points. Now I write a two corollary, easy corollary. So assume XL is a polystable, then there is an idyllic Fourier subharmonic matrix minimize Mabuchi functional height. Why? Because my height is the limits of this thing. Each of them non-negative, so I get a minimize this thing. So satisfy constant scalar curvature equation for each points. This gives a non-negative analog of system theory of a canonical matrix. Okay, so this is really the easy consequence from my paper. But unfortunately, my paper written for number theories, never written for algebra geometry. This should be easy consequence. But funny is nobody ever took this thing from my paper. So now I consider the constant family the case stability. Well, if I take my XL as a constant family, that's exactly the Donner's and Fukaya invariance discovered maybe 10 years later after my paper. And then there's a law boundedness of Mabuchi equal stability. So that's really special case of my paper, but for constant family. So finally, for number theories, this is something I really want to do. I'm a number theorist. I'm not I use algebra geometry, but in my heart, I'm a number theorist. So as I said, Archimedean place and periodic place should combine it together. If we want to prove the Yau's conjecture is supposed to prove a periodic and complex simultaneously without using PD. That's the whole point I want to say. And this suggests the framework, the counter geometry and arithmetic geometry combined together. The major open problem in this direction will be arithmetic system theory canonical matrix. If we go to my paper, I prove something, but not good enough. I prove the highest, it bounded below from some harmonic numbers. The number, unfortunately, is negative. I had a conjecture it should be positive, but so far, after 30 years, nobody knows how to prove it. So there's a dictionary. I want to say there's a degeneration problems in algebra geometry or in arithmetic geometry. This leads to stability. Then this leads to canonical matrix. This is something people are looking for. And in my talk, I introduced non-Euclidean geometry, trying to solve these problems. So this diagram shows three pictures: the geometry analysis, birational geometry, and the arithmetic geometry. Thank you.
Great, so that's very nice talk. I still remember the days when Yuan Xinyi, who works on this in Harvard in 2010. So I still enjoy the discussion how to look at Calabi conjecture over periodic field or whatever you call it. And I think it's fascinating to develop into this subject. Well, actually, Manin told me that's important before he died. Anyway, any questions? Yeah. Yeah.
Okay, thank you very much. This is a very interesting framework. So my question is how to describe the convex property in this geometry.
So if you give you a complex variety, then they're trying to make a small deformation so that the variety will define a number field, right? This is not difficult. Then of a number field, then you formulate a problem. You have a complex Cayley-Einstein equation. You have a periodic Cayley-Einstein equation. Already, I don't have an equation. I only have a functional, right? This is another thing, I mean, the equation is maybe I can write the equation. It's a Montan pair equation, so I can write it. So then the whole this approach is that okay, you want to prove the system conventional metric, you want to show there's a Mapuche function bounded from below. That's the key thing you do. But you don't know how to prove it. What can I do is I add all the Mapuche functions together. Then this become a number. You don't need a reference points to do that. So in this case, you have some other intersection theory, some other method to show this bounded from below. This was my dream about 30 years ago. So that's why I stopped working on that, because after I proved the negative number, I feel very depressed. So I said, okay, forget about subject. But many years later, everybody doing something different. So it's a one project. I'm not sure I answered your question.
Because when you're using the stability to prove the existence of solutions of some fully nonlinear equations, essentially you need to get some convex.
My proof pretty is
some functional.
Yeah, you're looking for my paper. My paper is quite easy. The 2 pages. You put some lines there. It's different thing. It's a global. So it's now a variety of a base. It's a curve. Exactly proof is a lecture. So use a global geometry. All is a variety. So you don't really use a variety of a complex number. They suddenly become I need another lecture to answer your question. Okay. I didn't looking for PDE.
Okay, thanks.
Okay, other questions? Yeah.
Professor Zhang, in your abstract of your report, you mentioned that in your 1993 letter to Deligne, you discussed the curve case.
Yes.
Yes. I never read that letter, but looking back today, which ideas from that period still carry over to today's adelic metrics, and which ones?
Okay, the story that
replaced by newer techniques.
Yeah, this Deligne pairing is invented by Deligne, right? So that's the important thing. I wrote to him, and then the same year I gave a talk in Max Planck, Bonn. So in June 2nd. So if you go to the Max Planck, you still can find my talk there. Describe how Deligne-Manford's degeneration should be the analog of the Klein metric. So I define a functional. I say this both situation minimize the Mapuche functional. And then I think many years later, the Donaldson formulated this called Futaki-Donaldson invariance. That's something like this is a metric. This is a special case I did it before. And no, I didn't stop working for 30 years. And I also apologize. I never checked the reference, what's going on in the last 30 years. But right now, as I find, I know that it's completely proved. So it's, my idea is not useful anymore. But at least I tell you, probably have another idea to prove this stuff.
Thank you.
Other questions? Well, as I mentioned, Manin wrote to me actually many years ago, saying that the Klein metric should be the part of the of geometry. I should look at all this over P. And I never did because I was too much involved in Calabian Miller symmetry in those days. But I think it's interesting to develop string field over periodic field also. And so presumably we could develop something over there. And Candela, many people has developing it, and so is our faculty, Kong, Janet Kong, who has been talking about it. Yeah. Okay, thank you. Great.
It's my great pleasure to introduce Sylvester, Professor Sylvester James Gates, to give a talk. This look like the physics, how 2D SUSY quantum field theory uncovered by basic representations. Okay, thank you.
Shall I sit or stand? You're the chair. Which would you prefer?
You can sit.
I prefer to sit. So first of all, I wanted to thank Professor Yau and all the organizing committee for this invitation to come and speak to you. This is my second visit to Beijing. I was here in 2008, just before the Olympics, and there was lots of construction underway. And Professor Yau, for me, like a lot of the young people and not so young people in the audience here, has been a leading guiding light in terms of thinking about mathematics at its highest levels. As I said this morning, I am not a mathematician. I'm a physicist, and I'm very aware of my disability when it comes to talking about mathematics. So I'm going to ask you in advance to forgive me if things are not clear. Ask questions. I'm happy to talk about my work. And so let me get started. As actually has been covered in this conference, a lot of progress occurred around string theory, which was really the early 80s into the middle 80s. And I was a new assistant professor at MIT in that period. And but I was studying supersymmetry. It's a form, a lot of people know about supersymmetry, but supersymmetry in quantum field theory was relatively new when I began my studies. In fact, I had an opportunity to write MIT's first PhD thesis on supersymmetry. And so defending my thesis was incredibly easy because none of the faculty members knew anything about what I was doing. I highly recommend this to young people. It's a way to make sure your defense goes very smoothly. But by the early 80s, string theory was starting to come to prominence. And I was in the group of Professor Daniel Friedman, who was one of the inventors of supergravity. And Dan one day challenged me. He said something like, you know, that superfield stuff, and I'm going to talk about superfields, is not the most transparent way to understand this subject. And so that sort of got me a little bit concerned because, you know, you're assistant professor. You don't want to hear your senior professor saying they don't think you're following the best path. So my response was I wanted to respond to the challenge. And that's basically what this talk is about. So anyhow, let's get started. So like I said, I would like to thank the committee for this opportunity. So everyone has heard about string theory, but there's something very strange in the history of string theory, which is that it had a pre-life that almost no one talks about. There was a physicist by the name of Daniel Friedman who did something really incredible in 1980. And this is before the string theory society comes into being. So let's start there. It was in the study of nonlinear sigma models, which is a subject that both mathematicians and physicists study consistently, but with very different languages. This slide actually defines a nonlinear sigma model in the way that we physicists think about it. Namely, in principle, a nonlinear sigma model can exist in an arbitrary number of dimensions. There are some field variables, and then there is a function that defines the Lagrangian for the energy of the system. Now, these sorts of models actually started in the 50s and 60s with Murray Gell-Mann, when they were trying to study the strong interactions of pions. So this is a very old, it's an old subject in that, but applied to very different physics. Daniel Friedman in 1980 did something utterly remarkable. What he did was show, this is actually supposed to be two-dimensional. What he did is made the following observation, that if you take the conventional sigma model and restrict D to 2, and I ask you to forgive my missing index here, and then go ahead and quantize the theory. You can calculate the quantum corrections to the theory. And when you do that, a most amazing thing happens. Namely, the quantum corrections take the form of what you see here. Now, what's amazing about this result is at least when I first saw it. The theory did not know that it should lead to the Riemann curvature tensor. The typical way that we physicists put these functions in, we calculate the renormalization, and something comes out on the other side. So it is an incredible accident, or something we don't understand very deeply about a quantum field theory, that by simply putting this function here and following our usual quantization procedures, the answer for the renormalization winds up with a Ricci tensor there. And if you continue to work to higher powers in the quantization, you find powers of the Riemann curvature tensor occurring. Now, what this shows, the most incredible thing about this, remember, this is before people talk about string theory. It's just ordinary quantum field theory in 2 dimensions. And if you demand conformal invariance, then all of these corrections have to vanish. And in particular, I'll come back to this term in a moment. But if you can get rid of this term, then the quantum corrections of this theory are Einstein's field equations. And it's totally accidental. You didn't tell the theory that you were doing general relativity. You just put the functions into the sigma model, you do the standard quantization procedures, and then out pops the condition that if the sigma model is sitting at a conformal point, that is a point where there are no corrections, you get Einstein's equation. Now, when I first saw this as a young assistant professor at MIT, I was utterly astounded, because this means that even if Einstein hadn't lived, if we had done enough quantum field theory for long enough, we would have actually discovered Einstein's field equations coming out of quantum mechanics. So this is one thing. So let me talk about this leading term, which is sort of the troublemaker here. You'll notice that this constant t, you can think about that as the Planck's constant. And so if you're going to take a classical limit of this theory, you would take t equals 0, in which case you would say, aha, the first quantum correction really is Einstein's equation. But this term blows up. So this term, turns out, there's no way for you to eliminate this as long as you deal with a non-supersymmetrical theory. And so this is, in fact, where supersymmetry makes its incursion, namely that if you set up the supersymmetrical analog of this, and I'll do that shortly, and then repeat these very same calculations, this term by supersymmetry is set to 0. And then you really see Einstein's equations. It's like, as I say, it's like magic. You just turn this machine, turn the crank, and then suddenly Einstein's equations come out. So let me talk about the supersymmetric analog, and this will bring me to the introduction of superfields, which is really where, when I was an assistant professor, it's really the thing that I cut my eye teeth on in understanding supersymmetry. So the idea of superfields, which was started, by the way, by Abdus Salam and a Kiwi named George Strathty, who was Salam's student. They're the first people who said, if you want to realize supersymmetry, what you need to do is think about functions that depend on some bosonic variables, and we can denote those by signals, but by sigma, as well as a set of anti-commuting numbers. And if they're anti-commuting numbers, it means you think of a power series Taylor representation. And so these things cut off very quickly in these extra coordinates. And then you're left with functions of the ordinary variables, and you can treat those by ordinary rules for quantization. So that's basically the idea of a superfield. Now, in superfields, so that's what these things are here. The leading component of this is, in fact, the variable that we saw in the original construction by Friedan. So you can see that there are other objects that occur. And so these other objects that occur in the system, are a set of fermions. You can think of these things as being sections of the spin bundle of the manifold over which the x's are the coordinates of the manifold. So you get spinors in the system. This is a massless Dirac Lagrangian that you see here. And then you also get a term which is quartic in the spinors. And these quartic terms, again, as if by magic, because you don't tell the theory this, you calculate these things from first principle, you find the Riemann curvature tensor occurs. Now, this is the supersymmetric version of the work that Friedan carried out. And this particular model also was used by Witten and Alvarez Gomez in looking at anomalies for higher spin systems just prior to the hysterical interest in string theory. I was a student and I remember watching this. And so that's supersymmetry. You do the quantum calculations here, and you find that that first term that was proportional to 1 over t is no longer the part of the calculation. So that's what caught my eye, is that suddenly Einstein's equations come for free. You don't tell the system that they have to have general covariance. You calculate in this system, and it tells you that it has to have the form of general covariance. So once you know about supersymmetry, you can ask questions about, well, gee, what I just showed you are the simplest supersymmetric models. The way to think about that is, if I was talking about Lie algebras, the simplest non-trivial Lie algebra is A3 or A2, namely what we physicists call SU2, A3, what we physicists call SU2. And so if you had a theory that had an SU2 symmetry, and you would just say, well, gee, how can I generalize this? Then the next thing you would do is you go to SU3. And so you can do the same kind of argument for these superfields. You can say, how can I complicate them? And when you do that, you start to get the simplest way to complicate things is to complexify everything inside. So you complexify the superfields, you complexify the Grassmann coordinates that the field is over, and then you ask yourself, can I write a sigma model? The first person to do this was Bruno Zumino back in 1979. And because you have these extra Grassmann, no longer, in fact, this is the thing that I've written here is the only thing that leads you to the model that contains the n equal 1 limit that we first saw. And so you see that this complexified potential turn is the line in that. Do what we call, we have to take the expansion and we integrate out the theta variable. And when you do that, you find out you get diversified. You have 2, we only had 1. Now, as this was actually Bruno. And what's really interesting here is that the metric that you, and this is an output. I keep going back to this is an output, not an input. The metric that you get K is conjugate. And also you have to impose on the condition. You have to pose a condition that whatever that function is, you want to have this as this term as a part of the limit, because you saw that in the simple case. Now, you can define a Kähler form as the function here times the differentials of the field variables, and the Kähler condition is exactly what it expected to be from studying algebraic geometry. So that's where I entered the story as a graduate student. All of the information that I just showed you was known. And Dan had made this statement, not this Dan, but Daniel Friedman had made this statement about using superfields. And so I was determined to show that no, superfields actually can tell you things that you don't get by looking at components. So I'm going to give you the answer of what I and some of my colleagues found. And basically, I'm going to show you a new action. So the bottom line from this new action is what we're going to be able to do is to show that there is a modification of the n equal 2 action, which I just showed you was the naive complexification, that when you look at the terms that you consider the sigma model terms, you find that there's a second-rank antisymmetric tensor involved. It's typically called the B field. And so I wrote the first paper where this was actually derived as a single author paper in 1980. I was a new assistant professor at MIT, and I was worried about what Dan had challenged me with. So suddenly, there is this second-rank 2 form, and then when you actually work out the details of the components here, what you find is that, remember the X variables here act as the coordinates of a manifold. These spinor variables act as sections of the bundle of the tangent of the spinor bundle over that manifold. And then what you find is that in order to calculate the derivatives here, you find a covariant derivative, which is the pullback of the tangent space of the x's to the two plane, and the Christoffel connection, which was there before. Let me go back. The Christoffel connection actually shows up in this thing. When you do it with this modified theory, you find out that you find two different Christoffel connections, as well as this three-form coupling to the spinors as if it's part of the Christoffel connection. And this is a signal that the theory has suddenly produced torsion. Because when you take the difference of the Christoffel connections, by definition, that's the torsion of the manifold. So it was clear to me when I wrote this first paper that suddenly the conventional wisdom was going to be broken, because when I had faced this challenge, the conventional wisdom is that two-dimensional supersymmetric sigma models all had to be Kähler. But we know Kähler manifolds are Riemannian manifolds. And so this thing clearly could not be a Kähler manifold. And in a second paper, working with Martin Rocek and Chris Hull, we actually did the calculations completely to see at the nonlinear level, was all of this actually the case? And it turns out it was precisely the case. And so this thing, with this modification, which I have quite not told you about at a fundamental level, produces two complex structures. So each complex structure squares to minus the Kronecker delta. The complex structures actually commute. If you actually think of them as matrices and calculate their commutator, it vanishes. The Nijenhuis tensor for both of these complex structures actually vanish. And each complex structure is covariantly killed with respect to the light cone direction that the covariant derivative is covariantizing in. So this very strange structure emerged from someplace. It was not something that anyone had ever seen before, and that's the meat of my first point about this lecture, is how in the world do you get to this? Because there's no obvious way, at least I didn't think there was any obvious way to this, and we had this theorem that said you couldn't do this. So let me go to that part of the story. It turns out that there's a kernel, and I'm sorry about this misspelling, there's a kernel in this system that we need to look at and think about what is the kernel here. And so let me tell you what we can do. The phi superfields, so-called chiral superfields, for both the derivative associated with the right moving direction in the two-dimensional plane and the left direction in the two-dimensional plane, these derivatives annihilate this object phi. So they are sort of a kernel of the system. In fact, you can sort of think of these like Bianchi identities in a gauge system. On the other hand, this object chi, you can see that that's not quite the case. So we can compare these two lines. For this superfield, this is the same as that. But when we look at these two lines, we see suddenly you put the complex conjugate on the derivative operator, and therefore the kernel of this system is different. So this is what I did in the first paper that I was describing, where we showed that there was this two form. In that paper, I explicitly made this change. And I want to talk a little bit about how that came about, because I think it's some pretty interesting mathematics that goes on. This is a lesson about how we might find more, ultimately more systems with mirror symmetry, and I'll come back to that at the end of my talk. So this thing was well known before I decided to take a whack at this system. This was something new. So we called this object a twisted chiral superfield. And now I'm going to back up a little bit, because I told you that this concept of the superfield began with Abdus Salam and John Strathty. So I'm going to go back in time a little bit because this is stuff that I had just learned in graduate school. And now we're writing a superfield not in 2 dimensions, but in 4 dimensions. You'll notice in comparison to what we had before, at most 2 of these anti-commuting variables showed up in the expansion. Now 4 of them are, because these spinners have grown. A 4-dimensional spinner is twice as large as a 2-dimensional spinner. So the expansion in the so-called Grassmann variables gets larger. And that brings more field variables. So I've indicated them here. So these extra field variables were well known in the original, were actually, this set of equations is actually in the paper by Salam and Strathty where they introduced superfields. And so what you can ask is, what are the component fields that are in this system? And so there is a scalar, there is again, one section of the bundle, but now the spin bundle we're talking about is the spin bundle over the 4-dimensional space, not over the target space. And then there's another scale, 2 scalars. There is a 1 form. We physicists like to put indices over on everything. I've learned in talking to mathematicians, this is not a nice thing to do, but I hope you'll forgive me because this is, like I said, taken directly from the original paper of Strathty and Salam. And then you find that there's actually you can think of this as the exterior derivative of another spin zero field that we call B. So this is in the original paper by Strathty and Salam. But because there are these higher order terms, you find that there is a second spinner in the system, and now sort of an exterior derivative of the first spinner, and then finally 1 new field up at the top order, and the second derivative of the field that occurs at the bottom. And as I said, this all comes from the original paper of Salam and Strathty in '72. So I had just finished learning this stuff. By the way, I was a weak interaction phenomenologist as I decided to change my mind. So I had been studying things like CV and CA. I don't know if there are any phenomenologists, but before we knew about Glashow-Weinberg-Salam theory, there was this whole, I see at least one person shaking their head. There was this whole formalism set up to try to understand weak interaction phenomenology. And so in my first year as being a graduate student, I decided I wanted to change, and supersymmetry became the thing that caught my interest. So how does the mathematics of the Salam-Strathty construction, which is how I found these things, what was I actually looking at? Well, so let me go back to the Salam-Strathty construct. At the time they wrote their paper, we actually knew that there were 2 independent representations contained in that single object. And so one of the representations contains only A, F, G, psi, and that's it. Whereas that 1 form that we saw was in the initial expansion is actually part of a different irreducible representation. So we knew from the original works of Salam and Strathty that expansion that they were working with actually was 2 distinct irreducible representations. So in my first paper in this subject, I decided to go back and do some, well, let's see what I did. So again, let's get our mathematics straight here. 1 collection of fields that transforms under supersymmetry consists of this set. Second set of fields that transforms under supersymmetry consists of this set. These are all functions of 4-dimensional space. You can think of the A, B, F, and G as maps from the 4-fold manifold into the real numbers. As I mentioned, the functions A are actually the components of a 1 form over the manifold. And the 1 form turns out to be a U1 connection. Also, that's actually very important to know that it's not just the 1 form, it's a gauge U form. It's a gauge field. So this is the knowledge that we started with, and then there are these 2 spinners. So in my first paper, I decided to do something I hadn't seen in the literature, which is to study the projection of these representations to lower dimensional manifolds. So we're going to restrict the representations and then decompose under the subalgebras by first going from SO13 to SO12. Now, when you do that, a lot of interesting thing happens. For example, we're going to restrict the representations of those field variables. And when you do that, the first thing that happens is that 1 form that you saw initially turns into a three-dimensional one form plus a scalar. We can do this projection here. We see it, but we don't have to stop there. We can actually project down, killing two extra dimensions. And what that actually does is produces two scalars. And now that one form in two dimensions has a field strength, and since it is a gauge field, every non-gauge invariant piece of information is actually contained in the field strength of that one form in two dimensions. So you can replace specifications of the dynamics by looking at that field strength, and that's this quantity W. So this is now the representations I get by starting with a Salam-Strathy and doing these projections on one of the representations. Now, when you look at these objects, you will notice that they look isomorphic. There are two scalars. There's a spinner, and then there are two additional scalars. And I should also say that there is a U1 there's a U1 number that we associate with these objects. We physicists call it the engineering dimension. And so these two objects have the same engineering dimensions as these. These two objects have the same dimension as these. And the engineering dimensions of these are different from those. And so you now have two different multiplets that look like they're actually isomorphic to each other. But it turns out they're not. And one way for me to explain that is to make an analogy. I can also do that projection down to one dimension as opposed to stopping at two. And if I project down to one dimension, then what I can look at is the orbits of the field variables under the action of the supersymmetry charges. And I can represent that by a diagrammatic object, which we call an adinkra. So our adinkras really are the orbits of the field variables under the action of the supercharges. And when you look at these two different objects that I've just introduced you to, under this projection, you find that there's only one difference. By the way, in these projections, this is a subject of adinkras, which is a whole nother thing that I would have to spend a lot of time to talk about in detail. Anyone who wants to know information about it, I'm happy to talk about it after and provide you with references. But basically, it is a graphical way to encode field variables. So when you look at these two objects, there's only one difference between the two, namely that here you see some solid yellow lines, and here those yellow lines are dashed. And the way that we have set up the conventions for the objects, when you have one of these graphical representations of the field variables and you change the sign of these lines, that is equivalent to saying that you have reversed the sign of the action of one of the generators. And so one of the generators from this reduction in comparison to the original theory has a minus sign in its transformation law. Let me make an analogy. I'm sorry, this should be SU2. And when I'm talking about SU2, another way to represent SU2 is to use young tableaus. And the two young tableaus I'm showing you here are the representation of what we physicists like to call quarks and the antiquarks. Now, these two representations are distinct. I'm sorry, it really is SU3. In SU3, these two representations are distinct. And so you can ask yourself the question, if I try to find the representation of the action of the generators of the Lie algebra of SU3 on these objects, what is the explicit form of those generators? We know that on the quark representation, you can look at any textbook, on the quark representation, the generators are 3x3 Hermitian traceless matrices. And these matrices it's usually for physicists are called the Gelman matrices. So what are the matrices that are representing the generators on the antiquarks? It turns out there's a way we physicists calculate them. I'm not quite sure how well known this is in the mathematical community, but Dan, you can help me out here. But the way we physicists look for the realization of the generators on the antiquarks is that we use an outer automorphism. That is, you can ask yourself the following question. The generators of SU3 satisfy a well-known commutation algebra. You can ask yourself, are there outer automorphisms? Namely, are there factors that I can that I can multiply the generators by that preserve the form of the commutation? That's what we mean by an outer automorphism in this context. And it turns out that, yes, you can find such an operation. And like I said, the way we physicists calculate it is we take the matrices, the usual standard Gelman matrices, we complex conjugate them, and then multiply by a minus sign. If you do that, you'll find out that this set of matrices satisfies the identical relationship before and after you've done these operations. So you have defined an outer automorphism. Now, the thing that's interesting about this outer automorphism is because of the form of the original matrices, 6 of the 8 Gelman matrices under the action of this automorphism are themselves. Only 2 of them actually change signs. And the 2 that change signs are the ones that define the maximal torus of the algebra. Now, why is that important? Well, the maximum torus of the algebra is precisely what defines the weight space of the representations. And so we can see that on the anti-quark representation, you change the signs of the coordinates in weight space, and that's the thing that tells you that you're looking at the anti-quark representation. It's a change of sign of 2 of the 8 generators. So what I will argue for you is that the change of sign that I'm showing you in that graphical representation of the 2 multiplets is the analog for supersymmetry for this observation about the SU3 algebra. Namely, that you get a different representation by looking for outer automorphisms in the action of the generators on the representations. So that's what I bumped into by accident as a graduate student, because I was simply looking at the properties of these things under projection. And now we can go backwards. Sorry. We can go backwards to this thing here. We now understand, oh, and by the way, that change of sign I was talking about is a consequence of the difference of these 2 equations right here. So this is what I mean, that the kernel actually makes a difference. So now when you work out the form of the component fields in this system, you find that thing that I showed you that had the torsion, that had these 2 complex, had these 2, suddenly blanking, had these 2 complex structures, has the torsion in the theory. It all originates by taking what you could have initially had here were two different phi's, call this set phi 1 and this phi 2. Then this would have been a Kähler theory. But by switching from phi's to chi's, you now have a theory that looks like a Kähler theory, except it has torsion. Now, when we found this result, and this is a result, as I said, I derived with Martin Rochek and Chris Ho. Martin was at Stony Brook and talking to Nigel Hitchen. And so Nigel became very interested in asking what's actually going on that these crazy physicists have actually found. What is it that this example of something that is almost a Kähler theory, but it has 2 independent commuting complex structures and it emits torsion. So it's not a Kähler theory. And Nigel actually, when we first understood these geometric descriptions of what we found, we called these things bi-Hermitian manifolds because they're Hermitian with respect to each of these complex structures, but they're bi-Hermitian because there are 2 complex structures. So Nigel did a really careful study of these models because they were things that were falling outside of what people had thought about was possible for Kähler systems. And he's the one who generalized this to what we now call complex geometry. This is work, for example, if you are familiar with the work of Galtieri, one of his students, is actually the mathematical specification of what I've told you here with respect to changing the kernel and finding these two complex structures and torsion in the model. So there's a lesson here that supersymmetry is smarter than we are, those of us who use it, because we never set out to find things in a purely mathematical description that would bring changes to the body of mathematical literature. Having discovered that these objects exist, spurred, as I said, Hitchin and Gualtieri to rigorously define these objects. And furthermore, because the relationship of Kähler geometries to CY geometries, it means that you can generalize CY geometry so that they also admit these sort of torsionful descriptions of manifolds. And that actually has been done also in the string theory literature. That was done by Andy Strominger and his collaboration. So the lesson that I take from this is that by using supersymmetric field theory itself as a tool, you can probe the trace of geometrical analysis without actually knowing any geometrical analysis. You simply follow the rules that are laid down by superfields, and they will guide you to these new discoveries, which you then probably have to figure out, what does this mean precisely mathematically? Because historically, this is exactly what happened. So we have other examples of these sorts of things. In our work with Rocek and Ho, not only did we just talk about these bi-Hermitian manifolds, a special class of these bi-Hermitian manifolds are actually hyperkähler. And so you actually start to see bridges to more and more complex structures in geometrical analysis by simply manipulating the structures of these fields. So the way that we get these hyperkähler structures is we use equal numbers of these objects, but now we put doublets here and doublets here. So therefore, that allows us to go from complex dimension 2 to complex dimension 4, which is what we need for the hyperkähler. And you can actually find expressions for the complex structures that form the SU2 algebra that you need for hyperkähler. It all comes for free. So I would posit that supersymmetrical field theory itself is an incredibly powerful tool for studying geometrical analysis, to discover things that were not known before. And the self-consistency actually comes from supersymmetry. That's a lesson that we learned. And so I am going to end here and tell you about something we haven't done, because it presents other opportunities. Remember, for what I've done and what I've presented to you, these sets of equations were the most important thing. Namely, that you take a representation of supersymmetry that you know, and then you ask yourself, is there an automorphism that I can introduce into this? If the answer is yes, then potentially you have found a new representation that's, roughly speaking, equivalent from going from the quark representation SU3 to the anti-quark representation. You now take this potentially new representation and you plug it back into the formula for the Lagrangian. If it yields something that hasn't been seen before, then you can rigorously check for using standard methods in geometrical analysis to see that it's all self-consistent. So what haven't I done? Well, it turns out that in some of my later work, I was studying Hopf indices and how they interact with supersymmetry. And so this process would be just what I did before, namely take a standard representation of the Hopf indices on a threefold, asked, can I write a supersymmetric Lagrangian describing the Hopf indices? In fact, there's a book called Superspace, which I wrote with Mark Gruseru and Martin Rochek and Warren Siegel. And in that book, we talked about supersymmetry in 3 dimensions. And if you look very carefully, you'll find the supersymmetric extension of the Hopf index is actually in that book. And that book, by the way, was written before I was a professor at MIT, assistant professor at MIT, looking at these questions about sigma models. So from that, I know that you can have simple supersymmetry, just like you could in the Hopf index, just like you can have simple supersymmetry for the sigma models. I also later showed that you could have n = 2 supersymmetry for the Hopf index, just like you can have n = 2 supersymmetry for the sigma model. So it's parallel construction. And now the question is, what plays the role of these equations? Well, it turns out for n = 2, we can find no such role where basically you're looking for an outer automorphism that preserves the supersymmetry algebra. We found that for n = 2, no such outer automorphisms exist. But curiously enough, if you go to the case of n = 4 supersymmetry, you find out these outer automorphisms do exist. And so that suggests that there's some interplay that I'm not aware of. And since you all are brilliant mathematicians, that suggests that there's some interplay between these new automorphisms and Hopf indices that will mirror what we have seen in sigma models. There's another lesson which I would like to sort of put before you. And that is, if I think about the supersymmetric representations as being the analogs of Young tableaus, let me do some calculations for you in your heads. If you calculate the dimension of that tableau with a single box in SU3, the answer turns out to be 3. If you calculate the dimensions using what we physicists call the Hooke's rule, for the 2 box, that also has dimension 3. So the quarks and the antiquark both have dimension 3. If you multiply the quarks, 2 quark boxes together, you will get a 6 and a 9, a 6 and a 3. And now if you calculate the dimensions, you find that 3 times 3 equals 6 and 3. But you could also multiply the 2 box representations, and you would find the same numbers. And so if you were just constructing polynomials by looking at powers of those representations in terms of Young tableaus, there's a kind of mirror symmetry. Namely, if you're just calculating the polynomials that depend on the dimensions, you will find that the single box ring of polynomials for all powers of the representation is equal to the double box multiplication for all powers of the representation. In other words, the infinite set of polynomials on these 2 representations are identical to each other. But the thing that we know that they're different is when you multiply the single box by the double box, you know that gives you a singlet and an 8. And so the polynomials are the things that tell you that these are the mixed polynomials are the things that tell you that even though you have these 2 infinite sets of polynomials that are exactly the same, when you look at the multiplication of one of the representations by the other, that's the thing that tells you that you're looking at different representations. And so I've defined for you a definition of mirror symmetry on polynomial rings of SU3 by this method. And so it is as a physicist, I don't know how to prove proofs, but as a physicist, I have a very strong suspicion that this definition of mirror symmetry may extend to other systems and gives an alternative way for you to even teach your students in a naive way what mirror symmetry is. And with this, I'll take questions.
Thanks, Professor Gates. Any question?
For the n equals 1,1 sigma model, what are the conditions for conformal invariance? I mean, for normalization? Is this spelled out in the literature?
Okay, so this is the n equal 1 theory. And you simply, like I said, you simply do, well, the tool that I and my friends like to use is supersymmetrical field theory. So you can do the quantization using superfields. And when you do that, you find out it produces exactly the same result, except for that leading term that Friedan found. So you just replace everything by superfields.
May I ask another thing? Yeah. So in the last part where you're proposing this other form of mirror symmetry, so you mentioned Hopf indices. I don't know what, can you say something about what?
Oh, sure. And let me see if I have something of that, because unfortunately, because the way I put together my talk, there are a lot of things. Okay. So here's one way to define the Hopf invariant measures. Consider maps from S3 to S2, and then write what we physicists like to call the Chern-Simons form, namely the gauge field, wedge D gauge field, which is a top form in 3 dimensions. So this is the, like I said, and this is very interesting. I'm sorry, I didn't realize I had put this in the talk. So you can say, as I said, so this is the standard conventional definition of the Hopf index. And so in the book that I wrote back with Martin and Mark Grisseroux and Warren Siegel, we asked ourselves the simple question, does this thing have a supersymmetric embedding? It actually does. These things are now superfields. You can tell because I'm integrating over theta. And you can work out the component form. And so what you find is that here's the standard Chern-Simons Lagrangian for the purely bosonic sector, and the spinor sector is actually trivial because there are no derivatives here, and so these are purely Grassmannian Lagrange multipliers. So there's no dynamics associated here. So this is what I mean when I talk about the Hopf invariance as opposed to indices. The question is, how much supersymmetry can I add to this? And what I've answered for you is I know how to do this up to n equal 4, and but in order to do it for n equal 4, the 2 different equations look like what I found for the sigma model case.
Thank you. Any more question? If no question, thanks, Professor Gates again. Okay, this concludes today's lecture. Tomorrow the lecture starts with 9:30. Yeah. Oh, one more lecture. Yes. Yeah, I have a jet lag.
Can I share a screen now? You can share a screen now.
It's my great pleasure to introduce Professor Motoko Kotani from Tohoku University, and she will talk about I-themes, recons, team. Oh, sorry,
No,
that's your
it's my
title.
affiliation though. Okay.
Where's the title?
This is the title.
Oh. Discrete surface and their convergence. Well,
So thank you very much. And so thank you very much for introduction. And it's my great honor and pleasure to speak here. The three names appeared in the title of the symposium. Leon Simon, S.T. Yau, and Karen Uhlenbeck are the shining star, were a shining star and still a shining star to me. And so I cannot say how much I'm excited to speak here. So my PhD study started in 1983. And so it means that my research interest has been developed in the picture history, which has been described by S.T. Yau in this morning. But my motivation is really based on differential geometry and geometrical analysis. But I'm inspired by more condensed matter physics or material science. It's a little bit different from Yau's case. But anyway, so I would like to introduce what I have been done last 20 years to construct a discrete version of geometrical analysis, especially very recently I'm interested based on discrete surface theory, which was inspired by material science. But before I start, I would like to show this beautiful crystal cube. So very recently, a friend of mine, who is not mathematician at all, gave a present to me, and she didn't know what is Calabi-Yau manifold, but she thought that it's a very beautiful engrave by laser. And so she just opens a box, here you are, and I was so shocked and surprised that this is Calabi-Yau manifold. And so I wonder how Yau is involved in this project or not, but anyway, you can buy this beautiful crystal cube through the website, and you can see from 3 different angles. Yeah, that's very good. Anyway, so it has nothing to do with my talk. Okay, so what is my motivation to study discrete objects? So, you know, the data is usually discrete. But when you would like to use the data, you would like to understand the property of data. Yeah. So for that, you need some kind of continuous information from the given discrete data. So how we can find the continuous information in a rigorous way or by using mathematics? And so in geometry, we can formulate the same question like this. So if you are given a discrete surface, the definition can be different, but if you are given a discrete surface, you would like to find a continuous surface behind that. So that is the question in how discrete geometrical analysis can contribute. So this is the bottom line is so this is the discrete surface I have been studying. It's a network graph. And so I put some color behind because if it's just a network itself, it's not easy to see. But there's no blue background for the given discrete surface. So you don't have this blue, very beautiful continuous surface. That's a discrete graph. But if you would like to study the property of when you would like to study the surface, especially geometrical property, it's much easier to find the continuous surface because when it is discrete, it's a really high dimensional object. But if we end solving discrete discrete equation, it's not easy, but if you find a continuous object, you can solve the PDE on the continuous surface and you just compare some geometrical object between discrete and continuous. So when we said the discrete analysis, we believe our life, our world is cosmos is continuum. And to describe the behavior or the motion or this shape, you find the PDE. And if you can solve the PDE, you understand everything RR. But usually it's not easy to get the explicit solution to the PDE. So the mathematicians do not mind it is so explicit, so we have an explicit solution or no, but when you would like to apply those the solution, the engineer or the people in the science, other than mathematics, would like to know more about this concrete one. And so that's how the numerical analysis get into the picture. And to use a numerical analysis, you would like to have a discrete approximation of the continuum model. So that was the picture, but now we know that the world is not continuum. It is our world consists of atom and molecule. So the real data or real world consists of discrete objects. But what we would like to understand is more like a continuum property, especially for the material or the condensed matter physics. So in this picture, what is important is to find a good approximation of in a continuum way. The reason I already described that if you know, as I said, the numerical analysis is very useful to understand the property of a PDE, the solution of PDE, but on the other hand, it really costs resources. Usually you cannot do the grand scale of computation by numerical analysis. If it is much easier to have some property from the continuum. And just you compare how the solution of continuum and the solution of discrete related, and then you can get information. So this is my motivation in last 20 years. Okay, so is the slide? Okay, now comes. So it's very slow. Okay, so I'm going to use the standard realization in several different contexts, but when we have this notion, it was joint work around 2000 to 2006, which was a long time ago, was a crystal lattice and random walk on the crystal lattice. And so this notion has been very useful, at least for us. So it's if it is three-dimensional, it has three directional periodicity, and the base is just a finite graph like this. And everything else is a copy of this finite graph. So it is a crystal lattice, and to mathematicians, it's an abelian cover of finite group. Anyway, so this is the object we would like to study. And I started working with him when he posed a question. So his question was very simple. There are three different graphs, two-dimensional graph. You see three picture upstream, and so it looks very different, but actually it's the same graph if you consider it's abstract graph. It has a vertex, and every vertex has three edges, and but the most canonical one to draw the picture of a hexagonal lattice. And as mathematics, I believe that most of the mathematicians choose most left side one because it's more symmetric one. And so his question is, when you are given arbitrary graph, just abstract graph, is there any way to realize given graph in a very standard way? And so when we respect the symmetry, of course, we can use the harmonic maps, and which actually the theme of my PhD study, and since harmonic map, minimal surface, and Laplacian are my main tool in the study of geometrical analysis. So because I have been working on harmonic map, I told him that if you would like to find the most symmetric one, why you don't use a harmonic map? And so actually it works. And for the periodic abelian cover, we can prove that there is a unique realization, and which is most symmetric realization in the sense that all the intrinsic abstract symmetry of the graph can be realized as the Euclidean symmetry. So that is the definition of most symmetric realization, and so that is the standard realization, and it's unique. And we don't know why it was useful to study random walk, but anyway, it works very well with random walk. So probably you know what is central limit theorem. So when you are given the random process or random walk, and then question is, does it satisfy a law of large number? And if it is the case, then what is the limit theorem, and what is the large deviations? And the crystal lattice is just a abelian cover of the lattice, and so it is not surprising that the periodic crystal lattice can satisfy central limit theorem. But our question is not to prove the central limit theorem of random walk on crystal lattice satisfies central limit theorem, but we would like to understand the central limit theorem in the way that it is the scale limit of the given process. So what do I mean? So if you have a random walk on crystal lattice, and we think it's the atom and the electric particle moving around the crystal atomic configuration, and so this random walk can generate the heat flow or electrical current or whatever continuum property of materials. And so this discrete version is the microstructure, and the heat flow of the Euclidean space or materials is a macroscopic feature. So we would like to understand the theorem, when you have a given discrete process and change the scale small and small and small and small, then eventually it converges to a kind of continuum object. And what is this continuum object and space? And what is the continuum process you reach? And so for that, so when you have a crystal lattice, which is actually the abstract object, but so there is no scale. There is no linear structure. It's just abstract graph. But when you embed it in the crystal lattice in Euclidean space, you can use the scale of the Euclidean space. But if you don't choose the proper realization in Euclidean space, the scale change does not fit in this picture. So only when you use the standard realization of abstract crystal lattice in Euclidean space, this central limit theorem can be understood like a scaling limit of the random walk converging to the Brownian motion or heat flow of a Euclidean space. So that is what we would like to do, and we don't still know why standard realization works very well in this picture, but standard realization is such a beautiful realization, most symmetric one, which maybe the nature choose, and somehow it works well, this random walk and convergence of the central limit theorem and large deviation. Anyway, so there are several versions, like when it is under the magnetic field, you can have a very similar object. So we can prove the central limit theorem under the magnetic field. In this case, even the equation is linear and periodic, but because of the magnetic field, it is not local analysis, but more or less we can manage to prove the central limit theorem in 2002 and 2003. And at that time, the standard realization really essential to prove that because of the non-periodicity. Anyway, so that has been done, and there are several extension and variation in this picture. So that is what I do with Professor Sunada. Yeah. So okay. So now I move to the why I have been working with material science and condensed matter physics. It's a very strange opportunity for me to be invited to the Center of Material Science. Also, and I was invited to become a director of this center. And so the name of the center is AIMR, Advanced Institute of Material Research, not mathematical research. But although it's a material research, I was asked to be a director. And why was it? Yeah, so the reason is very simple, which I already explained. So material scientists would like to discover or synthesize a useful material, which is continuum. It is used in our daily life, so it cannot be microstructure. It's a macroscopic feature. So the materials. So materials are like this. But nowadays you can control the atom configuration, and so how you gather the atomic configuration so that it exhibit a good property. That is the question. And the material very complex structure. It is atom, and atom will make atomic cluster and the network of clusters and several layer of the sizes. And so they would like to understand how these layers are connected. So in each layer, they have different description and different physical law, but important is how you can connect maybe go across the layers. So the question is that how you can find the continuum object, beyond the okay. So the question they would like to solve is that how the different scale can be connected, and I thought maybe we can use discrete geometrical analysis, which really make a bridge between micro and macro in the sense I already explained. And so when we started, because it is material scientist, and so we chose 3 topics to work together, and there should be important question to material scientists, and but also there are some mathematical tools which can be identified to be useful. And so today I'm not going to explain what they are, but the first one is non-equilibrium materials. And so when you work with the crystal, it's really like if you understand local structure, you understand all the global structure. If it is periodic like this, but they are very much interested in non-equilibrium material, and in that case, although they can take local pictures, but they don't understand the global structure, and so they would like to have a description of global structure from local data, although they have many local data, but they cannot configure how they can construct the global structure. So that was a question. And the second one is topological material. It was 2012, and so topological material, topological fields are very important in physics and applied physics. And so also, although it's a very fundamental question to physicists and the material science, but also it's like an index theorem. And so for mathematician, it's also very easy to communicate with them. So we took this is, and the last one is most related with my work and how you can find the continuum object from discrete data. So I'm most involved in the last one, the carbon network. And so that was the beginning of how I started working on the discrete surface theory. And so before I interact with the material science, I didn't realize the two-dimensional object is very important for them, because for mathematician, the lower dimensional is much easier. It's much easier. Two-dimensional is easier than three-dimensional, four-dimensional, higher dimensional. But for them, to make a lower dimensional object is a challenge. Usually the network just split in the three-dimensional. So how they can confine in the lower dimensional? That was a challenge. That's why those graphene and fluorine and those paid much attention. But I thought it's a good way to communicate with them to what is the challenge in the two-dimensional object which is discrete. And all these looks like a surface, but it's just a one-dimensional or the discrete object, and there is no definition when you find it's a surface. For example, if you are given the cubic lattice, so you don't think it is a surface. It's a three-dimensional object. If you are given the diamond lattice, you think it's a three-dimensional. But if you are given those charts, you think it's a discrete surface. So there must be the definition of a discrete surface. When you can consider a given discrete object to be surfaces. And there are many ways to define the discrete surface. And in the audience, I think Alexander Bobenko is there, and he's really a pioneer and a leader to study discrete surface. But this is our version. And so what is the definition of manifold? It's if you have a tangent space with n-dimensional space plane, then it's an n-dimensional manifold. So just like this, if it is the discrete surface, we can define the surface. It is a two-dimensional if it has a two-dimensional tangent space. So so what is the tangent plane? So given a vertex, so this is a vertex, and just the nearest neighbor, and the nearest neighbors, if it is only 3, then it can determine a plane uniquely. But if it is more than 4, usually in general, it cannot be defined a two-dimensional plane. So our definition of a two-dimensional object or discrete surface is just it's a trivalent graph, and of course non-degeneracy is assumed, but just the definition is if you have a two-dimensional tangent space which consists of which is defined by the nearest neighbor vertices. So that is our definition. And so we can, because we would like to do geometry, we have to find curvature, and we just define the shape operator, and then get the trace and the determinant to define mean curvature and Gauss curvature. And to convince people it's the right definition, we have to prove the area deformation formula. The reason why we consider mean curvature and Gauss curvature important in the surface theory or submanifold theory, it is because of this area formula. So without this, we cannot convince people it's a good definition, and we can prove. Okay, so this is a discrete surface theory we established with Professor Naito and Professor Omori. But our question is not just define the discrete surface theory, but to find the continuous surface behind the given disk surface. And so how we can do that? If you have a Riemannian manifold and you have a network on the Riemannian manifold, you usually take the, for example, the network is a triangularization, then you just make a finer and finer triangularization, and eventually it converges into a Riemannian manifold. But in our case, we don't have this nice the structure behind. If we have a nice Riemann surface, we can subdivide the given discrete network, but that surface is our target. If we know what it is, we don't have to work on that. We don't have a Riemannian surface. And so it's just abstract graph, or it's a graph realized in Euclidean space, but it's a lower dimensional. So we cannot use the linear structure of Euclidean space, which we did in the crystal lattice. And so we did 2 steps. And so first we subdivide the topological structure or combinatorial structure because it's a trivalent graph. Its dual is a triangle, and it's a planar graph. And the part of the graph is always a planar graph. And so you can just subdivide by using this so-called Goldbach-Coxeter subdivision. It's just the local structure, and we would like to realize this local structure in R3. And so now we use standard realization, and it again works very well. And so we kind of prove the convergence to a surface. And so this is the kind of discrete minimal surface, and you take this 2-step subdivision, and it just really converging to a real minimal surface, a classical minimal surface. But there is some singularities. But the singularity is very important because the first initial graph consists of mostly from hexagonal, but there should be octagonal because of the topological constraint. It's a negative curve. And so this octagonal face is so-called topological defect, and around topological defects there are very important interesting phenomena appeared. And so for the material science to mark singularity, topological defect is very important. So what we have at the end as a limit, it looks like a very smooth surface with singularity, and this singularity are very important, and we shouldn't avoid this singularity when we discuss. And so also we define the discrete curvature, and it converges into a classical curvature at the end. So this is kind of a numerical test, and some part are mathematics. But anyway, so the singularities are important, and we realize when you started with Flaren, which looks like a sphere or a positive curve, it produces many singularity. Actually, it's dense singularity at the end. But when you start with minimal surface, which is very balanced, and then you don't have singularity. That is the numerical test. And so in general, we have a three different kinds of singularity, but we would like to avoid the singularity which are not very important. So these singularity we would like to avoid. And so we realize the reason why we don't have a singularity for this so-called discrete Mackay crystal, which is a discrete version of minimal surface. And so the balance condition or harmonic condition are very important. So we decided to work with general discrete surface, but so-called discrete harmonic surface. And so so we can prove the convergence to the minimal surface when it's given the harmonic surface. But we are not satisfied to this very abstract subdivision and convergence theory. We would like to study more detail, and then the why minimal surface, classical minimal surface are important and also can be analyzed in the detail is Weierstrass representation. You don't have to understand what is Weierstrass representation, but if we are given two holomorphic data, you can construct a minimal surface. That is the crystal Weierstrass representation of classical minimal surface. If we have the same things, we can describe the discrete minimal surfaces and the convergence of these the series of minimal surfaces that we would like to have. And so actually before we do, and still there are several different groups who are working on discrete minimal surface. And so again, Bobenko has a big contribution, and there are many other people from different interests, different motivation. But anyway, so discrete minimal surface has been studied in some sense. And in our case, we just follow the Bobenko and the Pinkers, and by using this the holomorphic differential. So of course the graph do not have holomorphic structure, complex structure at all, but somehow there is a notion of holomorphic differential which satisfies this condition. And so this notion was defined by the discrete surface theory for their case. It cannot be just cannot apply to our case. It's a different surface theory, but we just borrow their idea, or it's really very similar idea to define the holomorphic differential. And so we are lucky to have a discrete version of Weierstrass formula. If you know what is Weierstrass formula, this the equation 1.1 is very similar and very natural discrete version. And so, but to have this representation, we don't work on the discrete minimal surface, but the discrete harmonic surface. Because isometry is just too strong condition for discrete surface. So we use harmonic surface, which satisfies some kind of balancing condition. And so we expect we don't have too many serious singularity to start. And so we start with discrete harmonic surface and construct a family or series of subdivided discrete harmonic surface by using this method we introduced or established, and then it converges into first of all it converges into the minimum. The limit is not the harmonic, but it's a minimal surface, and the geometrical data, discrete and continuum, can be very comparable. And so it's just a numerical things, but this is the object we construct, and it's like n per surface. And when you make a finite structure, it converges into minimal surface and the mean curvature going to 0. And there are many things. So how many minutes do I have? 4 more minutes. Okay, okay, I have to go. Yeah, so now I'm working on weaving structure. Weaving is like a cloth, and so you have infinitely many lines, and they are not interact each other. So there are red one and blue one, and there's no interaction at all. It's a collection of infinitely many lines. But somehow, when the blue and the red entangle, it really behave like a two-dimensional object. So how we can describe the structure and how you can define the this two-dimensional object. And so the so the model is like this. So in plane you have a square lattice, and all the x axis direction is blue line, and all the y axis direction is red line, and each intersection or vertices you are given the information about over and under. So if it is over and under, the red one is beyond above the blue one. That is the information we have. So this is the information, and some vertices red is above blue, and some blue and red. And between the different color vertices, there are some kind of impulsive force which just go forward, moving forward between two vertices. But between with the same colors, there are kind of harmonic oscillator which has the effect of coming closer. So this is the data you have, and by using this up and down, you define the height function. And you can solve the energy minimizing solution. So energy is defined harmonic oscillator and impulsive between the height function, the same different color of vertices. So the question is, you can find a stable configuration of weaving. First of all, how you can define the layer or connected component. As I said, it's not connected at all. It's just different the lines, but because of this up and down and the entanglement, there are somehow component which cannot be separated, and we define the non-separable component. We call it a layer, and we can define the notion of weaving connectedness, and connected component of weaving connectivity is exactly the same as a non-separable layer. And so in each layer, we can prove there is the stable configuration, which is the solution of minimizing solution of a given energy. And between two different layers, they push away each other. And so they are going to be moving apart in the order of T 1/3. So that is what we prove. And so although it is not two-dimensional, but some layers really looks like a two-dimensional object, and it has a stable configuration, which is minimizing energy. Okay. So that we proved by Naito-san, Sakata-san, and Shinka-san. There are many other applications in the example to work with material scientists, but thank you very much for your attention.
Any question? Yes.
Thank you for your talks. I have a question. I remember in one of your slides, you talk about the relation between discrete surface and the interval system. What is the dimension of that interval system? 2-dimension or 3-dimension?
Working on interval system, he is working on that.
For surface, two-dimensional. Oh, okay, 2-dimension.
Yeah, so my case is trivalent, but his case is more like 4 degree because of the integral system. You need kind of a coordinate x and y because to define the integral system. I'm just exaggerated to simplify the anyway. So that is what we have been doing.
Any more questions? Where?
What does it mean for material scientists that we find a discrete manifold structure in such things? What does it mean for material scientists?
Yeah, so they always would like to discover a new material or synthesize material. And so they would like to first to have some, not exactly the exact configuration or exact component of atoms, but they would like to know what could be the effective of dopant and things like that. For example, we work with material scientists, so they have a graphene, which is very flat. But they would like to have a reaction field. So they would like to have a curved part so that it can be a reaction field. And so they make this curved surface to dope different species. But what kind of dopant and where and how dense how the layer this dopant should be. So we use the standard realization with impulse effect and to tell how it should be should curve. It's not the exact analysis, but first it gives some idea. And the molecular dynamics, which is a simulation, a very precise simulation, coincidence with our prediction, and so they produce that material. And so that is a typical thing. So mathematics cannot go into the detail or exact the calculation, the prediction, but give some idea. And the molecular dynamics simulation can test our idea. And then because of the simulation, the experimental science has a motivation to really synthesize the structure. That is the typical way to collaborate with materials.
Thanks. Any more questions? If there are no more questions, let's thank Professor Kotani for a beautiful lecture.
So this is the last lecture of today.
Yes, yeah. Sorry, this is really the last lecture. Okay, see you tomorrow at 9:30.